Something strange happens when you stop and observe. A particle vanishes, a wave collapses, and suddenly what was possible becomes just one outcome. Where does reality go when no one's looking? Tonight, we drift into the quiet puzzles of quantum physics, the kind that still leaves scientists awake at night. Before we begin, tell us in the comments, where are you watching from? And what time is it right now? We're always curious who's listening, and when. If you enjoy falling asleep to science, press the subscribe button, and let your next dream start with a question. Now close your eyes, let the noise fade, and follow the mystery. Chapter 1. The Double-Slit Experiment. Where reality splits. Imagine standing in a quiet lab, late at night. There's no hum of voices, just the click of instruments, the quiet buzz of electricity, and the blinking red light of a detector. In front of you is a simple experimental setup. Just a board, a screen, and two tiny openings carved into a metal plate. It looks simple, almost too simple. Yet what happens here will shake the foundations of what we think reality even is. The double-slit experiment begins with a single question. What is light, really? Is it a wave, like ripples in a pond, or is it a stream of particles, like grains of sand? Physicists once believed it had to be one or the other. After all, our minds like clean categories. A thing is either this or that. Not both. Not something in between. So the first step is to shine light at a barrier with two slits, just like two narrow doorways side by side. Beyond that barrier is a screen that captures where the light ends up. You might think if light is made of particles, it'll go through one slit or the other and land in two distinct bands. But what you actually see is something much more curious. A striped pattern, alternating light and dark bands, a wave interference pattern, as if the light went through both slits and then interfered with itself. You can do this with light, with electrons, with atoms, even with molecules so large you'd never think of them as having wave-like properties. And yet, the result is always the same. Instead of forming two bright spots behind the slits, you get a complex set of light and dark bands, the signature of a wave. These bands are not just a blur or some artifact. They're real, measurable, predictable. To make it even more strange, you can slow down the experiment. Instead of firing a whole stream of photons or electrons at once, you can fire them one at a time. Just one particle. Just one tiny messenger of energy. You'd expect, with no other particles to interact with, it would just choose one slit and move through like a little bullet. But as you collect the dots on the screen, they begin to cluster in bands. The same interference pattern slowly builds up. The particle, it seems, acts like a wave, even when it travels completely alone. It's almost as if that single particle travels through both slits simultaneously, interfering with itself as if it were a ripple in water. But that doesn't make any sense, does it? How can a single, solid, indivisible thing go through two places at once? How can something behave as though it's in multiple positions until it's forced to reveal just one? This brings us to the heart of the quantum mystery, because what happens next is even more unsettling. Physicists thought, let's find out which slit the particle actually goes through. Let's install detectors at each slit, delicate instruments that can track whether the particle chose the left or the right. But the moment you do that, the interference pattern disappears completely. The banding vanishes. Instead of a wave pattern, you get two simple clusters, the kind you'd expect from a particle going through just one slit or the other. In other words, the act of observing the particle, simply knowing which slit it went through, fundamentally changes the outcome. It's not a small change, it's not a subtle influence. The entire nature of the result shifts. The wave-like interference is gone. Reality chooses a single path. The system behaves differently, purely because we asked it a question. This is the mystery. A particle behaves like a wave, existing in all possible states, until it is measured, and then, and only then, it collapses into a single definite outcome. The double-slit experiment isn't just about light or electrons, it's about how information shapes the physical world. At this point, you may wonder, what exactly causes the collapse? Is it the measuring device? Is it the recording of the data? Or does it require conscious observation? Some interpretations of quantum mechanics suggest that observation doesn't just influence outcomes, it defines them. That the very act of becoming aware of a result changes the state of the system. This makes the double-slit experiment not just an experiment in physics but a deep philosophical puzzle, because it touches on the boundaries between matter and mind, between physical phenomena and subjective awareness. Some scientists argue that consciousness plays no role, that measurement alone, even without a human observer, causes the collapse. Others argue that without awareness, measurement is meaningless. It's still a hotly debated topic. The Copenhagen interpretation, which dominated early quantum theory, states that particles exist in a superposition of all possible states until they're measured. The wave function, which describes all these possibilities, collapses into a single outcome when a measurement is made. But this explanation doesn't clarify why or how the collapse occurs, only that it does. Then there's the many worlds interpretation. According to this view, the wave function never collapses. Instead, every possible outcome plays out in its own branch of reality. The particle goes through both slits, and the universe splits in two, one where it took the left path and one where it took the right. You only experience one of them, but the others continue on, forever diverging. This interpretation removes the mystery of collapse, but replaces it with an infinite set of branching realities. Another interpretation is pilot wave theory, also known as the de Broglie-Bohm interpretation. It proposes that particles do have definite positions and paths, but they're guided by an underlying wave that determines where they go. The particle doesn't need to be in two places at once. It just rides on a complex field that guides its motion. This preserves a more classical picture of physics, but requires the existence of hidden, non-local forces. What's important is that all these interpretations make the same predictions. They describe the same experimental result, but the stories they tell about reality are wildly different, and none has yet been proven superior. This leaves the door wide open, not just for debate, but for imagination. It also leads us to a difficult truth. In quantum physics, what we observe is deeply tied to how we choose to observe it. That's not just poetic, it's mathematical. And it means the classical idea of a world out there, solid, predictable, objective, may not hold at the deepest level. This isn't just an oddity of science, it has real, practical consequences. The very technologies we rely on, lasers, semiconductors, magnetic resonance imaging, all depend on our understanding of quantum mechanics. The double-slit experiment laid the groundwork for these discoveries, even though we still don't fully understand its implications. So, the next time you turn on your phone, or send a signal through Wi-Fi, remember, that signal wouldn't exist without our journey through this strange territory. Our modern world is built on principles that defy our common sense. We've harnessed mysteries we still don't truly comprehend. And yet, even after a century of quantum physics, the double-slit experiment remains one of the most elegant and disturbing demonstrations of how the universe behaves. A particle becomes a wave collapses into a particle, and the boundary between those two forms seems to depend on whether we ask a question. Chapter 2. Entanglement. The invisible thread across space. Two particles are born together, maybe from the same spark of light, maybe from the same collision in a chamber colder than space. However they emerge, they are not just similar, they are entangled. Their properties are connected in a way that seems beyond reason. Spin, polarization, momentum, these attributes are no longer separate. If one goes left, the other must go right. If one spins up, the other spins down. They are linked, not by force or tether, but by something quieter. A rule of nature that doesn't care about distance. Send one particle across a room, the other across the galaxy. Measure one, the other responds instantly. No signal, no delay, no opportunity for light or anything physical to travel between them. And yet, something happens. This is quantum entanglement, a connection that feels almost magical, except it isn't magic. It's math. It's measurement. It's been tested again and again in the real world. And still, we don't fully understand how it works. When Einstein first encountered this idea, he didn't like it. He called it spooky action at a distance. He believed the world was local, that objects should only influence each other if something passed between them. A field, a particle, a wave, something real, something physical. But quantum mechanics predicted otherwise, and in the decades that followed, experiment after experiment confirmed what Einstein hoped wasn't true. Particles, once entangled, behave as if they're still one system, no matter how far apart they drift. This effect isn't just a trick of statistics. It violates what's known as Bell's inequality, a mathematical boundary that separates classical theories with hidden variables from quantum predictions. In the 1960s, physicist John Bell proposed a test. If hidden variables existed, if particles carried secret instructions all along, then certain statistical limits would never be crossed. But experiments crossed those limits again and again, and more recent versions, with better shielding, faster detectors, and cleaner isolation, have only made the case stronger. No local theory can explain the results. The universe doesn't behave as if things are separate. It behaves as if space itself doesn't matter, that once particles are entangled, the concept of distance becomes irrelevant. Measurement here changes reality there, not by sending a signal, but by revealing a connection that was always there, hidden, waiting. You can't use this connection to send information. Entanglement doesn't let you talk faster than light, but it does mean the outcome of one measurement depends on the other, in ways that defy logic. It's as if the two particles share a single story, and when you read one page, the other has already changed. This isn't just abstract theory. Entanglement is real. It's been observed with photons, electrons, even small molecules. In 2022, the Nobel Prize in Physics went to 3 scientists who pioneered experiments in entanglement, not just proving it exists, but showing how it defines the boundary between the classical and the quantum world. And we're using it. Right now, engineers and physicists are building systems that rely on entanglement, quantum cryptography, quantum networks, quantum computers, machines that store and manipulate entangled states to perform calculations beyond the reach of classical technology. In quantum teleportation, for instance, a particle state can be transferred from one location to another, not by moving the particle, but by using entanglement to recreate its exact quantum information at a distance. The original is gone. The copy exists. It's not science fiction, it's real. It happens. Just not to humans. Not yet. And yet, there are deeper questions. If entanglement connects particles across vast distances, then what else might it? Some physicists suggest space-time itself might arise from entanglement, that the geometry of the universe, the smooth curvature of space and time, might emerge from billions of microscopic entangled relationships. In this view, entanglement isn't just a strange feature of quantum systems. It's the glue, the foundation, the thread that knits reality together. Space might not be what separates things, it might be the structure that results from their connection. This is more than poetry. In a branch of physics known as added CFT correspondence, or holographic duality, equations suggest that space-time, percure and gravity emerge from patterns of entanglement. The more entangled two regions are, the closer they seem. The less entangled, the more distant they become. So in a strange and subtle way, entanglement may define nearness and farness, not distance in meters or miles, but in quantum relationship, a bond, rather than a gap, a closeness that isn't measured in space, but in shared information. And there's more. Entanglement isn't always between just two particles. In larger systems, chains of entanglement can link many elements together. An entire quantum computer is a web of entangled qubits. If even one qubit collapses out of sync, the whole computation can break. This raises new possibilities and new fragility. Entanglement is powerful, but delicate. Exposing a quantum system to the environment, to light, heat, or noise, can destroy the links. Decoherence, it's called. The system collapses into a classical state. The magic vanishes. The quantum world hides again. So scientists must build extreme conditions, supercooled chambers, total darkness, isolation so complete it borders on absurdity, all to preserve the ghostly threads that tie these particles together, all to keep entanglement alive just long enough to use it. But no matter how hard we try, we still don't fully understand what it means. Entanglement challenges the boundaries of what's real, what's separate, what's knowable. It breaks the idea that the universe is made of independent parts. It hints at something holistic, something inseparable. One measurement here, one change there, and somehow, the fabric of reality shifts. Not just metaphorically, but mathematically, tangibly, measurably. It's like plucking a string across the universe and hearing the echo immediately. No delay, no travel, just connection. And this leads to a haunting thought. If tiny particles can be entangled, then what about larger systems? Could you entangle atoms? Could you entangle memory? Could you entangle memory? Whether birds navigate magnetic fields with quantum coherence, whether human consciousness might in some elusive way rely on quantum links within the brain. No answers yet, just questions. Beautiful, unsettling questions. Because in the end, entanglement isn't about breaking the rules of physics. It's about discovering that the rules are stranger and more elegant than we ever imagined. So the next time you feel far from someone or wonder how a system can act as one even when split in two, remember, distance is only one way of measuring separation, and sometimes the deepest connections are the ones you cannot see. Let's move deeper now into the next quantum mystery, the eerie idea that a thing can exist in many states at once until it's forced to choose. Chapter 3. Superposition. Reality before the choice. In our ordinary world, objects obey a rule. They are in one place at a time. A coin is either heads or tails. A cat is either asleep or awake. A light is either on or off. This is the logic we live by, the logic we trust. But in the quantum world, that logic bends. It doesn't break. It bends. Quietly, gently, but undeniably. Superposition is the word we give to this strange quantum state, a state in which a system can be many things at once, not just uncertain, not just unknown, but truly multiple, until a measurement forces it to become one. The mathematics of quantum mechanics doesn't describe solid outcomes, it describes possibilities, a range of potential values, each with its own probability, floating like shadows in an invisible cloud. That cloud is the wave function. It contains everything the system could be, and in superposition, the system is all of them. Take an electron. It has a property called spin. Not quite like spinning on an axis, but similar in concept. It can be spin up or spin down. In classical terms, we'd expect it to be one or the other, even if we don't know which. But quantum mechanics says that before you measure it, it is in a superposition of both, spin up and spin down. At the same time, this isn't just a matter of being unsure. It's not a lack of knowledge, it's a lack of definiteness. The system isn't waiting to be discovered. It truly hasn't chosen, until the measurement. At that moment, the wave function collapses. The possibilities vanish. The electron becomes spin up or spin down. Not both, not anymore. This idea is more than a philosophical puzzle. It's been verified in experiments again and again. Entire laboratories are built to test and preserve quantum superpositions. In interference experiments, particles show evidence of having taken all possible paths simultaneously until observed. Consider a more visual example, the Mach-Zehnder interferometer. A single photon enters a beam splitter. It has two possible paths. In superposition, the photon doesn't choose, it travels both paths. When the paths are recombined, they interfere. The pattern that appears reveals that the photon existed in a blend of both trajectories. Only when we place detectors on the paths, trying to find out where the photon really was, does the interference disappear. The act of asking forces an answer. The superposition collapses. The magic hides. Perhaps the most famous thought experiment related to superposition is Schrödinger's cat. In this paradox, a cat is placed in a sealed box with a quantum device, a mechanism triggered by the decay of a radioactive atom. If the atom decays, a vial of poison is released, and the cat dies. If it does not, the cat lives. According to quantum mechanics, until the box is opened, the atom is in a superposition of decayed and not decayed. So the cat too must be in a superposition of alive and dead, not just unknown. Actually, both. This is absurd. It's meant to be absurd. Schrödinger proposed it to illustrate the strangeness of quantum theory when applied to larger systems. In truth, the cat is almost certainly not in a superposition. Decoherence, the process by which quantum systems interact with their environments, rapidly destroys such states. Large systems collapse almost instantly, but the core idea remains powerful. Before a measurement, the system is not one thing, it is many. In the lab, researchers have created superpositions in systems large enough to be seen with the naked eye. Tiny metal resonators, cooled to near absolute zero, have been made to vibrate in two directions at once. These are real, measurable effects. They require precise conditions, but they prove that superposition is not limited to abstract particles. Quantum computers rely entirely on superposition. A classical bit is either 0 or 1. A quantum bit, a qubit, can be 0, 1, or both at the same time. This allows quantum machines to explore multiple solutions simultaneously, solving certain problems far faster than any classical computer could. But superposition is delicate. Like entanglement, it is easily destroyed. The moment a qubit interacts with the outside world, through heat, noise, or light, it collapses into a definite state. The system becomes classical. the information is lost. To maintain superpositions, scientists build extreme environments, chambers that are colder than deep space, free of vibrations, shielded from all forms of radiation. Every atom must be kept silent. Every photon must be locked out. Only then can the quantum state persist. And still, we don't fully understand what superposition means. Does the system really exist in multiple states, or is it just a way of describing uncertainty? Is there an underlying reality, or is this the most fundamental level of truth we can reach? Different interpretations offer different answers. In the many worlds view, every possible outcome occurs, each in a separate branch of the universe. The wave function doesn't collapse, it just evolves. You, the observer, split too. In one world, you see spin up, in another, spin down. Both outcomes are real, you just inhabit one. In the Copenhagen interpretation, the wave function is a tool for calculating probabilities. There's no deeper reality until you look. The act of measurement creates the outcome. The world is fuzzy until we force it into clarity. Other theories propose hidden variables, or collapse mechanisms, or pilot waves guiding each particle, but none have gained universal acceptance. No interpretation removes the mystery entirely. Superposition remains what it has always been, the quiet tension between possibility and choice. So what is the universe before we measure it? Is it a cloud of maybes? Is it a field of branching paths? Or is it something we cannot yet name? Something that hides its truth behind the limits of perception? In the quiet moments before observation, the world holds its breath. Every particle balances on a knife edge of decision. Every atom hums with multiple possibilities. Reality hasn't decided yet. It waits, it hovers, it listens. And then something touches it, a photon, a charge, a conscious thought. Something crosses the threshold, and the wave collapses. One possibility becomes the truth. The others vanish, not as failures, but as unrealized dreams. The elegance of superposition lies not just in its strangeness, but in its power. It is a reminder that the universe does not always follow the rules we expect, that beneath the certainty of what we see is a foundation of softness, of ambiguity, of potential. The classical world is sharp, edges and lines, this or that, but the quantum world is gentle, blurred, overlapping, a song that plays all notes at once, until we listen, and when we do, it resolves into a single chord. But what we heard was only one version of the full harmony. Chapter 4. The Measurement Problem. When possibility becomes real, a particle floats in superposition, not here, not there, not in one state or the other. It exists in a cloud of probabilities. A wave function describes it, not as a location or a spin or a momentum, but as a set of mathematical possibilities, all of them real, none of them chosen. And then, something happens. A measurement, the wave collapses, one outcome becomes true, the rest disappear. But what is a measurement, really? Is it a machine clicking in a dark lab? Is it a camera recording data? Is it a scientist checking a number? Or is it something deeper, something tied to awareness, to consciousness, to the moment a result becomes known? These are the questions that form the core of the measurement problem, one of the deepest puzzles in quantum theory. The mathematics of quantum mechanics works beautifully. It predicts experimental results with stunning accuracy. Lasers, semiconductors, atomic clocks, MRI machines all rely on these equations. And yet, the theory doesn't tell us when or how the wave function collapses. It tells us what will happen if a measurement is made, but it doesn't define what a measurement is. This silence at the heart of the theory has led to decades of debate. In the Copenhagen interpretation, the wave function collapse is treated as a fundamental process. When an observation is made, the system selects one outcome randomly, according to the probabilities encoded in the wave. Before the measurement, all outcomes are possible. After, only one remains. But the Copenhagen view doesn't explain what qualifies as an observer. Is it any interaction with the environment? A detector? A human mind? The interpretation leaves that vague, almost intentionally so, as if it were better not to ask too closely. Niels Bohr, one of the founders of the theory, famously said that physics is not about what nature is, but about what we can say about enter. For some, this isn't satisfying. They want a clearer boundary, a mechanism, a rule. And so, alternative interpretations emerge. The many worlds interpretation, for example, avoids the collapse entirely. In this view, the wave function never reduces, all possible outcomes occur, but in separate branching realities. When you measure a particle's spin and find it pointing up, The universe split. In another version, it points down. Both results are real, but each in its own branch. You don't see the split. You live in it. Every quantum event becomes a fork in the road. Invisible, but profound. There is no collapse, only multiplication. This removes the need for a special rule for measurement, but at the cost of accepting an infinite number of parallel worlds, one for every quantum decision ever made. It's elegant in one sense, disturbing in another, because it suggests that reality isn't singular, but an ever-expanding tree of possibilities, each as real as the one you experience now. Still other interpretations, like objective collapse theories, propose that wave function collapse is a physical process, spontaneous, not dependent on observation. According to these models, a superposition becomes unstable as the system grows in complexity or mass. Eventually, the wave collapses on its own, without any need for measurement or awareness. In this framework, the classical world emerges naturally. Small systems can remain in superposition, but large systems like a cat, a person, a rock, collapse quickly. Decoherence plays a role here too, as the interaction with the environment causes the delicate quantum state to break down. But even decoherence doesn't explain why one result is chosen over another. It explains how superposition is lost, not how a single outcome is selected. And then there is the question that lingers, quietly, in the background. Does consciousness matter? Some physicists, a minority but a vocal one, have speculated that the act of conscious observation might be what triggers the collapse. That awareness, somehow, plays a role in choosing the outcome. This is not widely accepted. Most physicists see it as unnecessary, or even unscientific. But the idea persists, not because it's proven but because the alternatives remain unsatisfying. If measurement doesn't require consciousness, then what exactly does it require? What line must be crossed? What makes an interaction qualify as a measurement and not just another event in the quantum soup of the universe? No experiment has yet answered this. We can entangle particles, measure spins, isolate systems, but the precise moment of collapse, the instant when possibility becomes reality, still evades us. It happens, reliably, predictably, according to probability. But the why is still unclear. Some modern theories try to sidestep the problem by saying that collapse is just an illusion, that what we perceive as a single outcome is actually the result of entanglement with our own measuring devices, our brains, our environment, that we become part of the system, and that our version of reality is just one strand in a larger web. In this view, measurement is not a special event, it is just entanglement extended. The system, the observer, the instrument, all are bound together, and what we call collapse is really just the moment when we become unable to access other parts of the wave function, not because they vanish, but because they are no longer connected to us. This is the relational interpretation of quantum mechanics. It says that properties of a system are only defined relative to other systems. There is no absolute reality, only relationships. This sounds strange, but it might be closer to how the universe works, not as a fixed collection of facts, but as a shifting network of perspectives. In the end, the measurement problem remains open. It is not a failure of the theory. Quantum mechanics works perfectly well without resolving it, but it is a reminder that the theory describes outcomes, not causes. It tells us what we'll see, not what, and in that silence, there is room for wonder. Because the act of measurement, the moment of collapse, is not just a technical detail, it is the transition from what could be to what is. It is the line between possibility and presence, between all paths, and the one chosen. Every time you observe a quantum system, you take part in this transition. You witness the narrowing of the universe from many to one. You become part of the story, not just a spectator, but a participant, a node in the web, a co-author of the outcome. This is not meta. Chapter 5. The Uncertainty Principle. What the universe hides. There's a difference between not knowing something and being forbidden from ever knowing it. In classical physics, uncertainty is just a matter of limitations, of bad instruments, human error, or lack of information. But in quantum physics, uncertainty is not just technical, it's fundamental. The Heisenberg uncertainty principle tells us something astonishing. The more precisely we know one property of a particle, the less precisely we can know another. Not because we're clumsy, not because we haven't tried hard enough, but because nature itself doesn't allow both to be fully known. Take position and momentum, where a particle is, and how fast it's moving. In our everyday world, we treat these as basic facts. A ball rolls across the floor. It has a location and a speed. You can point to it, measure it, track it, But zoom in far enough to the scale of electrons or photons, and the rules begin to blur. If you measure the position of a quantum particle with high precision, its momentum, the product of its mass and velocity, becomes uncertain. If you focus on its momentum, its position becomes a smear. It's not that it's that it no longer exists in a sharp, single value. Mathematically, this is expressed in terms of a lower bound. The uncertainty in position multiplied by the uncertainty in momentum must be greater than or equal to a specific constant, Planck's constant, divided by 4 pi. This isn't a suggestion. It's not negotiable. It's baked into the structure of quantum reality. Imagine a wave. If it's a sharp spike, like a pulse, you know exactly where it is. But its frequency content is spread out. You don't know what notes are inside. If it's a smooth, continuous wave, one perfect frequency, you know its tone but not where it starts or ends. This is the heart of uncertainty. It's not random, it's harmonic. This limitation doesn't just apply to position and momentum. It also applies to other pairs of quantum properties, energy and time, for example. The more precisely you define the energy of a system, the less certain you are about when that energy was present. It's why short-lived quantum states can have fuzzy energy levels. The sharper the time window, the broader the energy spread. In quantum mechanics, every system is described by a wave function, a probability cloud, and that cloud is never fully confined. The more you try to box it in one dimension, the more it spreads in another. Nature resists absolute precision. It insists on ambiguity, not out of malice, but out of harmony. This principle has real consequences. It means that electrons in atoms don't spiral into the nucleus. If position and momentum could both be zero, if the electron could just sit perfectly still at the center, it would violate the uncertainty principle. So the electron must remain in motion, confined to orbitals with built-in fuzziness. This uncertainty creates stability. In fact, without the uncertainty principle, atoms wouldn't exist. Every electron would collapse into the center of the atom, and all matter would fall in on itself. But because of this quantum fuzziness, electrons are forced to hover in defined energy shells, creating structure, form, chemistry, life. And the implications go even further. In the vacuum of space, particles and antiparticles constantly appear and vanish, fleeting fluctuations allowed by the energy-time version of the uncertainty principle. These virtual particles are short-lived, but they influence real effects, such as the Casimir effect and Hawking radiation near black holes. This tells us something strange. Uncertainty isn't just a limit, it's a source of motion, of interaction, of energy itself. The quiet jitter of particles in empty space, what we call vacuum energy, is a consequence of quantum uncertainty. Even the void is never truly still. And yet, some people misunderstand the uncertainty principle. It's often misquoted as saying that measurement disturbs the system, that by observing something we shake it and lose information. But that's not quite right. The uncertainty isn't about disturbance. It's about the underlying nature of what exists. Even in a perfectly isolated system, with no observer, no light, no interference, the uncertainty remains. It's not created by us, it's revealed by us. And the deeper we look, the more it asserts itself. Physicists have tried to test the limits of uncertainty, to get around it, to refine it. But each attempt only reinforces the same truth. The universe is not made of hard edges. It is not built from absolutes. It breathes in waves, in trade-offs, in mysteries that protect themselves. Uncertainty can even be entangled. In quantum systems, you can create states where two particles share uncertainty in such a way that measuring one tells you something about the other, but never everything. The knowledge you gain is balanced by the knowledge you lose. This is not a flaw. It is a design. In quantum cryptography, this principle becomes a shield, because any eavesdropper trying to intercept quantum information will inevitably disturb the system. The uncertainty reveals the intrusion. This makes certain types of encryption unbreakable. In theory, are privacy protected not by keys but by the laws of nature. In quantum computing, uncertainty defines the space of possible operations. Every qubit lives in a cloud of potential values, each influenced by the limitations of measurement. Saputation becomes a dance between knowing just enough, but never everything. But perhaps the deepest lesson of the uncertainty principle is philosophical. It tells us that knowledge is always incomplete, that certainty is an illusion, that precision has a price. Every answer comes with a shadow of unknowing, and that's not a weakness, it's a condition of reality. We think of the world in terms of sharp outlines. A clock ticks, a particle moves, a thing exists, or it does not. But the quantum world offers no such comfort. It offers instead a canvas of probabilities, always changing, always hiding something just beyond our reach. And from that uncertainty arises form, structure, the music of atoms, the stability of stars. The universe, as we know it, exists, not in spite of what we can't know, but because of it. Uncertainty is not chaos, it is order of a deeper kind. So next time you imagine a particle floating through space, ask yourself, what do you know about it? Its position, its speed. The more clearly you try to define it, the more the other escapes. It's not just hiding, it's undefined. Not until you ask, and even then, not completely. Chapter 6. Quantum Tunneling. How the impossible becomes inevitable. Imagine standing before a mountain. You're a marble at the base, and the peak is tall, steep, and cold. You don't have enough energy to roll over the top. In the classical world, that's the end of the story. You can't climb the mountain, you stay where you are, no exceptions. But in the quantum world, the rules are different. In quantum mechanics, there's a strange and beautiful phenomenon known as quantum tunneling. It allows particles to pass through barriers that, according to all classical logic, they should never be able to cross. Not by climbing, not by jumping, but by simply appearing on the other side, as if the wall was never quite real to begin with. This isn't science fiction. It's not a rare or freak event. It's a core feature of how particles behave on the smallest scales. In fact, without quantum tunneling, stars wouldn't shine. Atoms wouldn't form. The universe as we know it wouldn't exist. To understand tunneling, imagine a particle approaching a barrier, a region of space where its potential energy is higher than its total energy. In classical physics, this would be a hard stop. The particle doesn't have enough energy to overcome the barrier, so it bounces back, rejected. But in quantum mechanics, particles are described by wave functions, mathematical expressions that extend through space and into the barrier itself. These wave functions don't stop at the edge. They decay, slowly, inside the barrier, like ripples fading into silence. And if the barrier is thin enough, the wave function continues to the other side, which means the particle might not reflect. It might tunnel. There is no classical path, no sneaky leap. The particle doesn't travel over the wall, it disappears into one side and reappears on the other. Not instantly, not magically, but with a probability that depends on the barrier's width and height. It's like a coin tossed against a wall, and occasionally found on the far side. This sounds impossible, but it happens. Constantly in semiconductors, electrons tunnel through junctions to create current. In radioactive decay, particles escape from atomic nuclei by tunneling through nuclear barriers, and in the core of stars, hydrogen nuclei fuse into helium only because of tunneling. Without it, the sun could not burn. You see, in stellar cores, temperatures and pressures are high but not high enough, classically, for protons to overcome their mutual repulsion. They should bounce away from each other forever, but quantum tunneling lets them slip through the barrier of electric repulsion and merge. This is how fusion begins, how light is born. Quantum tunneling isn't just a trick of theory, it has measurable, testable consequences. One of the earliest devices to exploit it was the scanning tunneling microscope, which allows scientists to image surfaces at the atomic level. By measuring the tunneling current between a sharp tip and a surface, we can see individual atoms. The resolution is not limited by light, but by the strange permeability of electrons. Tunneling also underlies phenomena like Josephson junctions in superconductors, systems where quantum effects operate on macroscopic scales. Supercurrents can tunnel across insulating gaps, creating delicate oscillations that form the basis for quantum sensors, magnetic field detectors, and even elements of quantum computers. These devices don't just rely on quantum effects, they are built from them. They function because of the rules that let particles cross forbidden zones. Without tunneling, the modern world would lose some of its most sensitive instruments. But tunneling also forces us to reconsider how we think about motion and presence. In classical mechanics, a particle travels along a path. You can track it, predict it, chart it. In quantum mechanics, there is no single trajectory. There are probabilities, amplitudes, and paths that seem to defy space altogether. One way to visualize this is through Feynman's path, integral formulation. In this view, A particle doesn't take a single path from point A to point B. It takes every possible path, simultaneously. And the result we see is the sum of all those contributions. Some cancel out, some reinforce. And in certain scenarios, paths that go through the barrier, paths that are forbidden in classical physics, contribute just enough to allow tunneling. This doesn't mean that the particle knows where the barrier ends. It means that its presence is never truly confined. That every location is a question of probability, not certainty. Even a barrier designed to stop a particle completely has a non-zero chance of failing. It may take time, it may be rare, but the possibility never vanishes. This has led to deep questions about how quantum mechanics handles time. How long does a particle spend inside the barrier? Does it slow down, speed up? Some interpretations suggest the particle doesn't travel through the barrier at all. It simply disappears and reappears. Others offer timescales that suggest the traversal is faster than light, though without violating causality. These aren't just theoretical games. In certain experiments, researchers have timed the process and found surprising results, but there is no universal agreement. Tunneling, like many quantum phenomena, resists classical interpretation. It refuses to fit into our timelines, our cause and effect reasoning. Even in philosophy, tunneling has been used as a metaphor. The idea that you can pass through a challenge not by confronting it head-on, but by subtly existing around it. That barriers are sometimes illusions, and the world's most rigid rules can bend under quiet persistence. And it leads to another possibility. Quantum tunneling might play a role in the origins of the universe. In some cosmological models, the universe began in a quantum vacuum, and tunneling caused a transition from one vacuum state to another, triggering the Big Bang. The universe didn't climb out of its initial state. It tunneled. Reality changed by slipping through the laws that defined it. If true, this would mean that the universe itself is the result of quantum instability, a rare event that unfolded because the wave function of everything found a path through the void, a tunnel through which existence emerged. Quantum tunneling reminds us that the world is not rigid, but boundaries we think are absolute may only be barriers in name, that energy, form, and even existence itself are more flexible than we ever imagined. A particle in a box can escape, a star in the cold dark can ignite, a wall can become a doorway, not by force, but by probability, not with effort, but with inevitability, not every time, not always, but enough. And perhaps this is the lesson, that what seems impossible may only be unlikely, that nature allows exceptions, not in defiance of rules, but as part of them, that there is always a non-zero chance of slipping through, of becoming something new on the other side. Chapter 7. Quantum Fields. Why the Vacuum Isn't Empty. Close your eyes and imagine absolute emptiness, no matter, no light, no sound. Just a pure, perfect vacuum, a nothingness so complete it stretches between the stars, beyond galaxies, beyond time. Now, let that image go, because in quantum physics the vacuum is not empty. It never was, and it never will be. At the heart of modern physics lies a radical idea that everything we see, every particle, every force, every flicker of matter is not fundamental. These are not building blocks, they are excitations, ripples, localized vibrations in deeper, invisible things called quantum fields. You've heard of particles, electrons, photons, quarks, but each of these corresponds to a field that spans the universe. The electron is not a point of matter drifting through space. It is a tiny wave, a localized wrinkle in the electron field. The photon, a ripple in the electromagnetic field, and so on. These fields are not theoretical add-ons. They are the stage and the actors, the fabric and the motion. Space is not an empty container. It's more like a vast ocean, filled with overlapping fields. Everywhere, even in the coldest corners of space, even between atoms, these fields hum quietly, always present, always active. The vacuum, then, is not nothing. It is the lowest energy state of all these fields. Not zero energy, not silence, but the baseline hum of reality. This hum gives rise to strange effects, like the spontaneous appearance of virtual particles, pairs of matter and antimatter that pop into existence and vanish again, all within the bounds of uncertainty. These are not science fiction. They are measurable, in phenomena like the Casimir effect. Two uncharged plates placed very close together in a vacuum experience an attractive force. Why? Because the quantum fields between them are restricted, and the imbalance in vacuum energy pushes them together, a force from nothing. And then there's the Lamb shift, a tiny change in the energy levels of electrons in hydrogen atoms, caused by interactions with the vacuum itself. These shifts are predicted by quantum electrodynamics, and measured to astonishing precision. The vacuum is not empty, it is active, alive with fluctuations. This is the realm of quantum field theory, or QFT, the framework that unifies special relativity with quantum mechanics. It replaces particles with fields. It describes creation and annihilation, not as magic, but as ordinary transitions in these underlying structures. The math is complex, the implications staggering. In QFT, particles are not little spheres, they are quanta bundles of energy, appearing wherever the field is excited, and these fields can interact, overlap, intertwine. Forces are no longer mysterious pushes and pulls, but the result of fields exchanging quanta. Electromagnetism arises from photons, the strong force from gluons, the weak force from W and Z bosons. Even the famous Higgs boson, discovered in 2012, is not a thing on its own. It is a ripple in the Higgs field, a field that pervades all of space. It is this field that gives mass to particles. Without it, the universe would be weightless, structureless, stillborn. What we call mass is not substance. It is interaction. Particles resist motion not because they are heavy, but because they couple to the Higgs field. The stronger the coupling, the greater the resistance. Mass becomes a form of participation, a kind of friction in the dance of fields. This view, that particles are not things but events, redefines how we think about matter. The electron you observe in one place is not a tiny ball that traveled there. It is the result of the electron field vibrating at a specific point. If the field is quiet, no electron. If it shakes, one appears. And it leads to a deeper truth. Space is never truly empty. The vacuum is not a passive backdrop, but an active player. Its fluctuations create force. Its structure defines what is possible. It is not absence. It is potential, the womb of everything. This may sound abstract, but it governs your reality. The light in your room comes from photons, field quanta. The warmth in your skin comes from infrared radiation. Another field, another ripple. The solidity of your chair comes from electrons resisting compression. Yet more field interactions. Even the atoms in your body are defined by quantum fields. The particles themselves are not building blocks, but fleeting patterns. What holds you together is not stuff, but structure. Stable arrangements in the quantum sea. And there's more. These fields don't operate alone. They're woven into a single mathematical framework, called the Standard Model. It's not perfect, but it's astonishingly accurate. Every experiment we've thrown at it confirms its predictions to remarkable precision. Every particle discovered fits the field-based mold. Yet even here, mysteries remain. Gravity, the force that shapes stars, galaxies, and the cosmos, still resists full integration. Unlike the other forces, we don't yet have a quantum field theory of gravity. The graviton, if it exists, has never been observed. And then there's dark energy, a form of vacuum energy that seems to accelerate the expansion of the universe. It behaves like a property of space itself, a quiet pressure, a whisper in the vacuum. Some believe it is the energy of the fields themselves, others think it points to something deeper. Quantum field theory also predicts an enormous amount of vacuum energy, far more than what we observe. This mismatch is one of the biggest unsolved problems in physics. Why doesn't the vacuum tear the universe apart? Why is its effect so small? What cancels it? What hides it? We don't know. But the clues lie in the structure of the fields, in their symmetries, in their vibrations, and perhaps in what they're made of, because quantum fields may not be the final story. They may be emergent, rising from something even more fundamental, strings, loops, or networks. But for now, the fields remain our best map. They show us a universe without particles, without emptiness, without silence, a place where even the void is full, a reality in which everything, light, matter, energy, is just the surface of deeper waves. And it leads to a profound idea. If the universe is made of fields, and fields are everywhere, then nothing is ever truly alone. Everything is immersed in the same invisible fabric. We are all ripples in the same sea, temporary disturbances in a timeless structure. Chapter 8. String Theory. The music beneath matter. Think of your favorite note, a soft piano key, a vibrating cello string, or the deep tone of a bowed bass. Now imagine that everything you see, touch, and know is built from similar vibrations, not sounds in air, but the vibration of something far smaller, far deeper, a string. In classical physics, particles are points, dimensionless, zero-size entities. They have position, mass, charge, spin, but no inner structure. In quantum field theory, particles are excitations of fields, brief ripples that appear and vanish. But in string theory, there's something more fundamental, something that vibrates. String theory proposes that what we call particles are not points but tiny one-dimensional objects, loops or segments of string, vibrating in different patterns. Each pattern gives rise to a different particle. The electron, the photon, the quark, all emerge from the music of these strings. The idea is both simple and radical. A violin string can produce many notes depending on how it vibrates. In the same way, a fundamental string can produce many particles depending on its vibration. Different modes of vibration correspond to different properties, mass, charge, even the force the particle mediates. But these strings are unimaginably small, far smaller than atoms, protons, or even quarks. They exist at the Planck scale, a size so tiny it makes a proton look enormous. If an atom were enlarged to the size of the solar system, a string would still be invisible, and yet this hidden structure might unify everything. String theory was originally developed to explain the strong nuclear force, but it soon showed signs of something deeper, a possible theory of quantum gravity, because one of the natural vibration modes of a string behaves like a graviton, a hypothetical particle that would carry the force of gravity. This is what makes string theory so compelling. It offers a framework that could unite all known forces, electromagnetism, the weak and strong nuclear forces, and gravity. A single theory that could, in principle, describe the entire universe, from the tiniest quark to the curvature of spacetime. But there's a catch. The math only works if the strings vibrate in more than 3 dimensions of space. In most versions of the theory, 10 or 11 total dimensions are required, 9 or 10 spatial, and 1 for time. This doesn't match what we observe. So where are the extra dimensions? String theory proposes they are compactified, curled up tightly at every area in space, too small to detect directly. Imagine a garden hose viewed from a great distance. It looks like a one-dimensional line, but up close you see it has width, a tiny loop wrapped around the length. In the same way, the extra dimensions could be coiled up in shapes known as Calabi-Yau manifolds. These curled dimensions don't just hide, they influence. The shape of these hidden dimensions determines how strings vibrate, which in turn determines what particles exist, how they behave, and even what laws of physics we observe. The universe, in this view, is like an instrument, and its geometry defines its song. This opens up a stunning possibility, that different configurations of compact dimensions could give rise to different physical laws, different constants, different particles, entirely different universes. In string theory, this collection of possibilities is called the string landscape, and it may be vast, even infinite. Each point in this landscape corresponds to a possible universe with its own physics. Most would not support life. Many would collapse instantly. But a few, perhaps only one, could lead to the structures we know: stars, atoms, minds, hours. This has led some physicists to propose the idea of a multiverse, a collection of universes, each with different parameters, each a different song played by the same set of strings. We might inhabit just one corner of this grand possibility space, chosen not by design, but by compatibility, by survival. But string theory is not without controversy. Despite its mathematical beauty and promise of unification, it has yet to make testable predictions. Its scale is beyond our current technology. We can't probe the Planck length. We can't detect the strings directly, and so, for now, the theory remains unproven. Some critics argue that without experiments, string theory is philosophy, not physics. Others point out that it has already deepened our understanding of black holes, quantum information, and the geometry of spacetime, even without direct evidence. Its mathematics has influenced entire fields. Its questions have sharpened our tools. One remarkable discovery is the idea of duality, that two seemingly different theories can describe the same physics. In ADNA CFT correspondence, for example, A gravitational theory in a curved space can be equivalent to a quantum field theory on the boundary of that space. It's as if gravity and quantum mechanics are two faces of the same structure. This duality suggests that space itself might be emergent, not fundamental but arising from deeper quantum relationships. That space-time as we experience it could be the shadow of something else, something encoded in entanglement, in vibration, in pure information. String theory pushes us to reimagine what the universe is made of. Not particles, but patterns, not matter, but music. And if true, it would mean that all diversity from atoms to galaxies arises from the same fundamental activity vibration. Each electron, each photon, each proton, a note played on a cosmic string, each interaction, a harmony, each law of physics, a rhythm written into the geometry of the hidden dimensions. We do not live in a clockwork universe, we live in a symphony. And in this view, you are not made of atoms, you are made of notes. Your body, your brain, your thoughts, all arise from the resonance of strings vibrating in fields shaped by invisible geometry. You are, in the deepest sense, a song being sung by the universe. Whether or not string theory proves true, it has given us a new lens, a way to see the universe not as static and fixed, but as dynamic and flowing, a process, a performance, and perhaps, somewhere in that performance, lies the key to unifying everything. Next we move to a phenomenon born in gravity, but tied deeply to quantum mechanics, black holes. What happens when space folds in on itself, when information disappears and maybe comes back? Chapter 9. Black holes. When space eats information, a star collapses, its light fades, its atoms crushed by their own gravity fall inward, deeper and deeper, until they disappear. What remains is not just mass, not just darkness, but a place in space where the rules begin to break down, a region where gravity becomes so intense that nothing, not even light, can escape. This is a black hole. Black holes are among the most mysterious objects in the universe. Predicted by general relativity, confirmed by observation, and now regularly detected through gravitational waves and radio imaging, they are real, and yet they seem to defy our understanding of space, time, and quantum physics. At their heart lies a paradox, a contradiction between the smooth, geometric world of Einstein's relativity and the unpredictable, probabilistic world of quantum mechanics. And that paradox begins at the edge, the event horizon. The event horizon is not a surface in the traditional sense. It's a boundary, a point of no return. Once something crosses it, a photon, a spaceship, a planet, it can never come back. Not because it's crushed instantly, but because the geometry of space-time changes. Inside the horizon, all paths lead inward. There is no out, and yet, from the outside, nothing unusual seems to happen. An object falling into a black hole appears to slow down, dim, and freeze, never quite crossing the horizon. Time stretches, signals redshift, reality flickers towards silence. But from the object's own point of view, it falls through in finite time, heading toward the center, the singularity. The singularity is where general relativity breaks, where the equations lead to infinities, densities beyond measure, curvatures beyond comprehension. It's a place where our laws of physics stop working, not because of some exotic condition, but because they were never designed to handle this. To make matters more puzzling, quantum theory tells us something strange. Black holes are not entirely black. In the 1970s, Stephen Hawking showed that black holes should emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, causes the black hole to slowly lose mass. Over time, it evaporates. This discovery was revolutionary. It connected thermodynamics, quantum theory, and gravity in a single equation. It gave black holes a temperature, an entropy, a sense of quantum life. But it also created a problem, a deep one. If a black hole evaporates entirely, what happens to the information that fell into it? In quantum mechanics, information is never destroyed. The evolution of a system is reversible. Even if particles interact chaotically, their full quantum description remains. You can, in theory, run the film backward, but if a black hole disappears, taking with it everything it once consumed, where does that information go? This is the black hole information paradox. It pits two of our most trusted theories against each other. One says information must be preserved, the other says it can vanish. And for decades, physicists have tried to resolve this contradiction. One idea is that the information is not lost, but somehow encoded in the Hawking radiation, that the radiation isn't perfectly thermal, as Hawking first thought, but carries subtle correlations that, taken together, preserve the quantum details of what fell in. This would be a monumental balancing act. Every particle emitted would carry a piece of the past. Another idea is the holographic principle, the notion that all the information contained in a volume of space can be described by data on its boundary. Applied to black holes, this suggests that everything inside the event horizon is encoded on its surface. The black hole's entropy, its quantum content, scales with area, not volume. This leads to the idea that the event horizon might not be a passive boundary, but an active surface, a kind of information screen, where everything that enters is recorded in fine quantum detail. Nothing truly disappears, it just gets rephrased. And then there are more speculative proposals that black holes connect to other regions of space, even other universes, through wormholes, that the singularity might bounce, creating a new universe on the other side, that space and time as we know them are emergent from deeper rules that preserve information in ways we can't yet see. Some researchers have proposed the concept of firewalls, violent surfaces at the event horizon that burn up any infalling matter, destroying classical assumptions to save quantum rules. But this raises more problems. The smoothness of space is lost. General relativity breaks in new and unsettling ways. Others believe the answer lies in quantum gravity, a theory that doesn't yet exist, but which would unite the geometry of space-time with the principles of quantum fields. Such a theory might show that information is preserved through mechanisms we haven't yet imagined, that evaporation is not the end, but a transformation. What makes black holes so haunting is their silence. They do not emit light. They do not reveal their secrets. They are the most efficient data compressors in the universe, and the most mysterious. They are places where space folds back on itself, where time slows to a crawl, where logic becomes negotiable. And yet we know they're real. We've seen their effects on stars. We've recorded the gravitational waves from black hole mergers, ripples in space-time itself. We've even captured the silhouette of a black hole's shadow, ringed by hot matter, spiraling inward. These aren't ideas anymore, they're measurements, and they point to a deeper truth, that black holes are not holes at all, but laboratories. Natural places where the universe runs experiments we cannot replicate, where gravity and quantum mechanics meet and clash. They force us to ask questions we're not used to asking. What happens to a person who falls in? Do they cease to exist? Do they live on, in scrambled form, in the radiation? Or do they re-emerge, somehow transformed? The answers are not known, but the pursuit has changed physics. It has given rise to new frameworks like quantum information theory, which treats particles not just as matter but as carriers of data. It has linked entropy to space-time. It has drawn unexpected bridges between computation and geometry. In this new view, space-time might not be made of coordinates and curvature, but of entanglement. That the very shape of space emerges from the flow of quantum information, that gravity itself is a consequence of entropic forces. A black hole becomes not a void, but a hard drive, a vault, a place where information gets twisted, but not destroyed. We're still learning, still probing, still wondering what lies beyond the event horizon. Perhaps we'll never know. Perhaps the answers lie beyond human reach. Or perhaps one day, a deeper theory will pull back the veil and show us the full picture, not just of black holes, but of reality itself. Chapter 10. The Observer Effect. Does the universe notice you watching? There's a moment in physics, quiet, brief, but deeply unsettling, when you realize the act of looking may change what you see, not metaphorically, literally. In the quantum world, the line between observation and outcome isn't clean. It's fuzzy, and sometimes it disappears altogether. This is the observer effect. The idea that measuring a quantum system can alter its state. The particle behaves one way before you look, and another way after, not because it was hiding, but because your observation caused it to choose. This concept sits at the center of quantum mechanics, and it's most famously illustrated in the double-slit experiment, where particles like electrons or photons create interference patterns when not observed, but act like particles when watched. The act of observation collapses a wave of probabilities into a single event. It turns maybe into this. But what counts as observation? Is it the moment a detector is triggered? Is it when data is recorded? Or is it when a conscious observer becomes aware of the result? That question leads to deeper waters, ones that blur physics and philosophy. In the Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and others, the wave function represents all possible outcomes. But when we measure, the wave function collapses. We no longer deal in probabilities. We deal in one result. But the theory doesn't say when collapse happens, or why, or whether it needs a mind to occur. Some early interpretations hinted that consciousness plays a role, that reality doesn't decide until a conscious observer looks. It's a troubling idea, because it puts the human mind into the equation in a way most physicists try to avoid. Science thrives on objectivity, on systems that evolve independently of us. Yet quantum mechanics keeps pulling us back. Over and over the same theme re-emerges. What we choose to measure determines what we see. Electrons behave as waves or particles, depending on how we observe them. At the quantum level, the question you ask shapes the answer you get. This doesn't mean your thoughts control the universe. It doesn't mean intention bends physics. But it does mean that quantum systems don't exist in definite states until they interact, and interaction in quantum terms is defined by measurement. But what is measurement really? Is it any exchange of energy? Any entanglement between a quantum system and the environment? Many physicists now believe that decoherence explains the transition, that when a quantum system becomes entangled with its surroundings, it loses its superposition, not by collapsing but by becoming part of a larger classical system. In this view, the observer doesn't cause the collapse, the environment does. The air, the heat, the photons bouncing around, they all nudge the system out of coherence. The observer simply becomes aware of what has already transitioned. This is cleaner, less metaphysical, but it still doesn't fully explain why one outcome occurs instead of another. This is where interpretations diverge. In many worlds, all outcomes happen. In branching parallel universes, the observer doesn't choose, In relational quantum mechanics, outcomes are only defined relative to the observer. There is no absolute fact. Only observed interactions. Still, the sense lingers that reality might not be entirely real until it's watched, or interacted with, or experienced. This is not just a curiosity. It challenges our understanding of causality, of time, and even existence itself. One experiment that deepens the mystery is the delayed choice quantum eraser. In this setup, a photon is sent through a double-slit apparatus, but before it's detected, a second photon, entangled with the first, is measured in a way that determines whether the original photon behaves like a wave or a particle. The twist, the decision to measure the second photon, is made after the first has already been detected. And yet, the interference pattern or lack of it matches the measurement. It's as if the later choice affects the earlier outcome, as if time itself bends to the act of observation. This doesn't mean backward causation. It means that in quantum mechanics, events are linked in ways that defy classical timelines. Some researchers argue that this isn't about retrocausality, but about entanglement and correlation, that the results are consistent, not magical. But even so, the implication is unavoidable. In quantum physics, the whole experiment matters. The setup, the question, the observer. You can't separate one piece from the rest. This leads to a provocative question. What is the role of consciousness in physics? Are we simply another system? Or is awareness in some sense a special kind of observer? Some thinkers, including physicists like John Wheeler, have speculated that the universe requires observation to exist. His phrase participatory anthropic principle suggests that observers may be necessary to bring reality into being. This isn't about human exceptionalism. It's about interaction, about relationship. In quantum mechanics, properties don't exist in isolation. They exist in relation to something else. You don't have a position until you measure one. You don't have an outcome until it's observed. Maybe existence itself is interactive. In this view, the observer is not outside the system. They're inside it, entangled with it. Reality is not a painting to be viewed. It's a conversation to be had. Every observation is a reply. Every measurement, a moment of co-creation. This doesn't make physics spiritual. It doesn't mean the universe is sentient. But it suggests that objectivity has limit, that the boundary between observer and observed is more porous than we thought, that the role of the observer is not passive, but structural, and it leads to a final mystery. Could consciousness itself be quantum? Some researchers have speculated that brain processes, especially those involving microtubules or quantum coherence, might operate at the quantum level. The idea is speculative, controversial, and unproven, but it touches a deeper intuition that mind and matter might not be as separate as they seem. Even if consciousness is classical, the observer effect remains. Our awareness, Our choice to measure one thing and not another shapes what becomes real, not in the mystical sense, but in the physical one. Measurement defines outcome. So the next time you stare at the stars or feel the pull of gravity beneath your feet, remember, your presence is not separate from the universe. You are part of its unfolding. Your questions define its answer. Your gaze shapes its form. Chapter 11. The Holographic Principle. Is the universe a projection? Reach out and touch the world, the chair beneath you, the walls around you, the sky above. It all feels solid, immense, three-dimensional. But what if all of it, matter, energy, even space, is not what it seems? What if reality is a projection? This is not metaphor, it's physics. A strange, serious idea known as the holographic principle, first hinted at in the 1990s and now explored in some of the deepest corners of theoretical physics. It suggests that everything we observe in our familiar 3D universe may actually be encoded on a distant, lower-dimensional surface. Imagine a hologram, a two-dimensional sheet of plastic, etched with patterns. Shine the right light, and a three-dimensional image appears. You can walk around it, look behind it, but the information, the instructions, are stored on a flat surface. The depth is an illusion, a mathematically precise illusion. The holographic principle proposes that our universe might work the same way, that what we experience as space, volume, distance, depth, could be emergent, not fundamental. That every object, every particle, even the fabric of space-time itself, might arise from quantum information encoded on a boundary we cannot see. The idea began with black holes. In the 1970s, physicists realized something strange. The entropy of a black hole, a measure of the information it contains, doesn't scale with its volume. It scales with its surface area. The event horizon, not the interior, holds the key. This defied classical logic. You'd expect a bigger volume to contain more information. But in a black hole, it's the outer shell, the horizon, that defines its content. This hinted that information in a region of space might be fully described by data on its boundary. In the 1990s, theoretical physicist Leonard Susskind, building on work by Gerard de Hooft, proposed the holographic principle, that all the information in a volume of space can be described by a theory that lives on the boundary of that volume. Not just black holes, but all space, everywhere, always. This bold idea found concrete form in a model called Ada's ECFT correspondence, proposed by Juan Maldacena in 1997. In this model, a universe with gravity, Ada's anti-de Sitter space, is mathematically equivalent to a quantum field theory, CFT, that lives on the boundary of that space. One is 3D, the other is 2D, but they describe the same physics. Think about that, a world with gravity, black holes, and curved space, all encoded on a flat surface, without gravity, like a cosmic drive, storing all of reality on its shell. A blueprint that contains not just structure, but dynamics, forces, even time. Abel CFT is a toy model. Our universe doesn't exactly match its geometry, but the implications run deep. It shows that gravity can emerge from a theory with no gravity. That space can be built from entanglement. That depth can arise from patterns of information. In this view, space-time is not a backdrop. It's a construct, a large-scale illusion, generated by deeper rules. Like temperature arising from the motion of molecules, space might arise from the arrangement of quantum bits, entangled across a surface we can't directly see. This also gives new meaning to black hole information paradoxes. If everything that falls into a black hole is encoded on the horizon, then nothing is lost. The information isn't trapped in the singularity. It's smeared across the surface, preserved in code. Some physicists now believe that our universe as a whole might be holographic, that somewhere, perhaps on the edge of the observable universe or on some mathematical construct beyond space, there lies a surface that contains the instructions. We are the image. That surface is the negative. This doesn't mean we're living in a simulation. The holographic principle is not about virtual reality or computer programs. It's about how nature may organize information. It's about dimensionality, about how reality can be emergent, not. And the idea connects deeply to entropy, entanglement, and quantum information. The geometry of space, in this view, might arise from how quantum states are entangled. The more connected two regions are, the closer they feel in space. Tear the entanglement, and the space between them stretches. This could explain why gravity behaves the way it does. In some models, Einstein's equations, which describe the bending of space-time, can be derived from the rules of quantum entanglement, not as an approximation, but as an exact outcome. Gravity in this picture is no longer a force, it's a shadow. And this leads to an unsettling conclusion. The universe may not be made of matter, but of information, that bits, not particles, are the true foundation, that physical laws are computational rules, that what we experience as solidity is simply the output of deeper logic, encoded on a distant, unreachable screen. Even time might be emergent. In some versions of holographic theory, time arises from how quantum information evolves. Past, present, and future are not fundamental directions, but reflections of deeper correlations. You aren't moving through time. You are part of a process. Unroll. The holographic principle also echoes ideas in quantum error correction, where information lost in one part of a system can be recovered from another. This might explain why black holes don't erase information, why gravity is robust, why reality seems so consistent, despite being built from something so fragile. Look, we don't yet know if our universe is truly holographic. We see hints, mathematical signs, patterns that suggest a boundary we cannot touch, but the evidence is indirect. The theory is powerful, but unproven. Still, it fits. It connects dots that were scattered. And even if the holographic description is not final, it teaches us something profound, that reality may not be what it appears to be. That dimension, distance, even existence, are concepts built on deeper laws, laws that care more about connections than locations. In the end, the holographic principle may not reduce reality. It may expand it. It shows us that the world is not fixed in place, but woven from relationships, that space is a language, not a substance, that the universe might be a code, self-executing, self-knowing, and endlessly unfolding. Chapter 12. The Quantum Vacuum. Why Nothing is Never Empty. Close your eyes and imagine true emptiness, not a quiet room, not deep space, but absolute perfect nothing. No atoms, no particles, no fields, no time. Just the void, a blank canvas, a clean slate. Now, open your mind, because in quantum physics, such emptiness does not exist. There is no perfect vacuum, no place that is truly empty. The void, it turns out, is alive, restless, teeming with energy, a silent storm beneath the surface. This is the quantum vacuum, and it may be the most misunderstood concept in all of physics. Far from being empty, it's a field of constant activity, a space where particles flicker in and out of existence, driven by the uncertainty at the heart of quantum mechanics. According to the Heisenberg uncertainty principle, you cannot simultaneously know the energy of a system and the time over which that energy exists with perfect precision. That limitation leads to a strange freedom. For very short times, particles with uncertain energies can exist, not permanently, but long enough to leave an imprint. These are called virtual particles. They are not directly observable, they cannot be captured or recorded, but they affect measurable things. Like the forces between real particles, they are not fantasy, they are structure, they are the scaffolding of the quantum world. One example of their effect is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they attract each other, not because of gravity or magnetism, but because of the pressure of virtual particles around them. Fewer fluctuations can exist between the plates than outside, creating an imbalance, and that imbalance pulls them together. This force has been measured, repeatedly, with increasing precision, and it confirms that the vacuum, even with no matter, no heat, no light, exerts pressure. It is not passive, it pushes, it breathes. Another place where the vacuum reveals itself is in Lamb shift experiments. In hydrogen atoms, the energy levels of electrons shift ever so slightly due to interactions with the quantum vacuum. This deviation matches theoretical predictions down to the tiniest decimal, and confirms that electrons feel the background hum of empty space. The vacuum also underlies spontaneous emission, the process by which excited atoms release photons. In classical physics, this release would require a trigger, but in quantum physics, the vacuum itself provides the nudge. The ever-present fluctuations act as a gentle tap, causing the atom to let go of its excess energy. Even quantum tunneling, which we explored earlier, depends on the vacuum. The ability of particles to appear beyond barriers, to defy classical confinement, is only possible because the vacuum supports probabilities. It is not a neutral stage, it is a player, a participant. The quantum vacuum also plays a central role in quantum electrodynamics, the theory that describes how light and matter interact. Here, virtual particles constantly mediate forces, ensuring that electrons and photons exchange momentum and energy in precisely calculated ways. These calculations agree with experiment to extraordinary degrees, sometimes to 14 decimal places. And yet, despite its accuracy, the quantum vacuum hides a terrible mystery. When physicists calculate its energy density, the amount of energy per unit of empty space, the result is enormous, mind-boggling. Enough energy, in theory, to rip the universe apart. But we don't see that. The vacuum appears calm, stable. The cosmological constant, the measure of how the vacuum affects cosmic expansion, is small, very small. This mismatch between theory and observation is one of the deepest problems in modern physics, a discrepancy of 120 orders of magnitude. It is, by far, the worst prediction in science. We don't know why. Some suggest there's a balancing force, others propose new physics. Some turn to the multiverse, suggesting that only in a universe with such a small vacuum energy could observers like us evolve, a kind of anthropic filter, a cosmic lottery. Whatever the explanation, one truth remains. The vacuum is not empty, it is the foundation of all fields, all particles, all interactions. Remove everything, and it remains. You cannot peel it away. It is the 0 point C from which everything rises. In quantum field theory, the vacuum is the ground state of all fields. Every particle is a vibration, but the field never stops humming, even in its lowest mode. These 0 point energies persist even at absolute zero, where classical motion ceases. The coldest object still carries the vacuum's fingerprint. And there's more. In cosmology, the early universe may have begun in a high-energy vacuum state, a false vacuum, and then transitioned through quantum tunneling to the lower energy state we now inhabit. That moment, called inflation, caused space to expand faster than light for a brief instant, smoothing and stretching the cosmos. This inflationary period may explain why the universe is flat, homogeneous, and filled with tiny fluctuations, the seeds of galaxies. And it all began not with something, but with nothing, with vacuum energy, with fluctuations in the void. In some theories, vacuum fluctuations don't just create particles, they create space itself, the expansion of the universe, the growth of time, the unfolding of dimension, all driven by energy from the vacuum. We are riding a wave that never rests, a sea that never sleeps. Even Hawking radiation arises from the quantum vacuum. Near a black hole's event horizon, virtual particle pairs appear. Normally they annihilate each other, but if one falls into the black hole while the other escapes, the escaping particle becomes real, and the black hole loses mass. The vacuum again becomes active. So when you hear the word nothing, remember, in physics it is one of the most dynamic and powerful concepts. It gives rise to matter, to motion, to life. The vacuum is not the absence of being, it is the potential for being. This changes how we think about existence itself. Reality doesn't sit atop a foundation of particles, or atoms, or strings. It sits on possibility, on fluctuation, on the constant, unrelenting dance of fields that never quite rest. Chapter 13. Time. Is it real, or just something we feel? Time feels natural, inevitable. The ticking of a clock, the rising of the sun, the soft fade from memory into imagination. We live in time, we move through it, we age, we change, we remember. But in physics, time is not so easy to define. Is time a thing? A dimension? A flow? Or is it simply how we make sense of change? Is it fundamental to the universe, or a feature of our perception? These are not poetic questions, they are scientific ones, and their answers remain uncertain. Let's begin with classical physics. In Newton's world, time is absolute. It ticks the same for everyone, everywhere. Past, present, and future exist in sequence, immutable and shared. It's a backdrop, like space, unchanging and universal. But Einstein changed that. In special relativity, time became flexible, a dimension, like space, that could stretch and bend, depending on your motion. If you travel fast enough, close to the speed of light, time slows down for you relative to others. It's not a trick, it's a measurable effect. Atomic clocks on speeding planes confirm it. In general relativity, time bends in the presence of mass and energy. Near a massive object, like a planet, a neutron star or a black hole, time slows down. Two identical clocks, one at sea level and one at the top of a mountain, will tick at slightly different rates. This phenomenon is called gravitational time dilation, and it's not hypothetical. GPS satellites orbiting Earth must adjust for it constantly. Without accounting for time's flexibility, your phone's location would drift by kilometers in minutes. So time, in Einstein's universe, is relative, it's personal. It depends on where you are, how fast you're moving, and what's near you. There is no universal now. The idea that two distant events happen simultaneously becomes meaningless. Instead, the universe is described as a four-dimensional fabric, space-time, in which all events are laid out. The past, present, and future are equally real. Like pages in a book, you read them in order, but the pages all exist at once. This view is called the block universe. In the block universe, time doesn't flow, it simply is. Our sense of moving through time from moment to moment is an illusion created by consciousness. From this perspective, the past and future are no less real than this moment right now. But if time doesn't flow, why do we remember the past and not the future? Why do we grow older, not younger? Why does a cup of coffee cool down, but never spontaneously heat back up? These questions point to the arrow of time, the one-way direction we all experience. It comes not from relativity, but from thermodynamics. The second law states that entropy, the measure of disorder, tends to increase. Systems move from order to chaos, from low entropy to high. A broken egg doesn't reassemble, smoke doesn't go back into the cigarette. The universe, in its grand unfolding, moves from simplicity to complexity, from smoothness to structure. This gradient defines our arrow of time. But entropy is statistical. It's not a fundamental law. It arises from probabilities. So the arrow of time might be a macroscopic illusion, emerging from the way particles organize themselves. It tells us more about systems than it does about time itself. Some physicists believe the universe began in a state of extremely low entropy, smooth, dense, and hot. That starting condition created a built-in directionality. As entropy increases, so does the passage of time. The arrow was born with the cosmos. But why did the universe start that way? We don't know. Others suggest time may be emergent, that it's not a fundamental part of reality, but a construct, something that arises from deeper laws. In quantum mechanics, the equations are time symmetric. They don't care whether time moves forward or backward. They work both ways. But our experience doesn't. This mismatch leads to theories that time could emerge from entanglement, from information flow, from the way systems interact and record history. In this view, time is not a river, but a record. Not something that moves, but something we assemble, moment by moment, from memory and measurement. Some models of quantum gravity, like loop quantum gravity or certain string theories, suggest that time might not exist at the deepest level. That space and time are built from something more fundamental, like discrete units of geometry or pure information. In these models, time isn't smooth. It's granular, constructed. Even in the Wheeler-DeWitt equation, which attempts to unify quantum mechanics and general relativity, time disappears. The equation has no time variable. The universe, in this picture, is timeless. Change still occurs, but not in a ticking clock-like way. Instead, the universe exists in a state where all possible configurations are encoded. Our experience of sequence is just a path through them. So where does this leave us? Time may be real, it may be emergent, it may be a feeling, a measurement, a direction, or it may be a human concept, one that helps us make sense of motion and memory in a world governed by laws that do not care. And yet, something about time feels different. We experience it intimately. We feel its weight, its flow, its rhythm. Time governs how we live, how we plan, how we remember. We are beings of time, structured by it, shaped by it, and sometimes ruled by it. But maybe time is not a thing that flows. Maybe we are the ones moving. Maybe each moment is static, and we're the projector, casting the illusion of motion onto the screen of the present. Maybe memory is the trick that makes the past feel real, and imagination the mirror that lets us see the future. Whatever time is, one thing is clear, it remains unsolved. Not just in physics, but in philosophy, in neuroscience, in our most private thoughts. We measure it, track it, manage it, but we don't fully understand it. Not yet. Chapter 14. What is reality? Beneath the surface of what we see. Look around you, the room you're in, the light on the walls, the objects resting quietly in space. It all seems stable, solid, undeniably real. But what is real, really? Is it the sensation of touch, the consistency of experience, the agreement between minds that something is there, even when we look away? Or is it something deeper, more elusive, something that exists independently of perception, observation, or thought? This question, what is reality, is not just a philosophical exercise. In physics, especially quantum physics, it is an open wound, a mystery that refuses to close, because the deeper we probe into the fabric of existence, the less certain we become of what we're even looking at. Let's begin with the building blocks. The atom, once believed to be solid, like a miniature billiard ball, it turned out to be mostly empty space. A nucleus, tiny and dense, surrounded by a cloud of electrons, not orbiting like planets, but existing in probabilities, locations smeared across a range of possibilities until you measure them. Zoom further in, you find that even protons and neutrons are made of smaller entities, quarks and gluons dancing in quantum fields. And those fields, they're not objects, they're patterns, vibration, mathematical structures with no definite position, just energy and probability. So the things we call particles, electrons, photons, quarks, are not little dots of stuff. They are excitations in fields, ripples in invisible oceans that span the entire universe. What you think of as matter is a peak in a wave. What you feel as solid is resistance to overlap. There is no substance underneath. And yet, everything we do is built on this illusion of solidity. We hold objects, build machines, touch the ones we love, all on a scaffolding made of emptiness and probabilities. This isn't poetic metaphor. It's experimental truth, verified in lab after lab, model after model. So is reality made of particles, or fields, or something else entirely? Some physicists believe that, at the most fundamental level, reality is made not of things, but of information, that what truly exists is the relationship between events, the logic of how one state leads to another, not the objects themselves, but the connection. In this view, often called the it-from-bit hypothesis, every physical entity is a result of binary decisions, measurements, outcomes, yes or no questions. The universe is not made of particles, it's made of answers. But who is asking the questions? Is it us, the observers, or is the universe constantly measuring itself in the form of interactions, entanglements, and collapses? Some interpretations of quantum mechanics suggest that reality only becomes real when observed. Others argue that it's always real, but only relative to something else. This leads to relational quantum mechanics, the view where reality is not absolute, but always relative. The spin of an electron is not a fixed property. It has no value unless it is observed, or more precisely, unless it interacts with something else. In this picture, there is no ultimate godlike observer who sees the full state. There are only interactions, and each one builds its own reality. It's like a web, endlessly connecting points. Each strand is an observation, each knot the shared truth, but there's no master loom, no canvas behind the weave, just the threads, dancing in tension with one another. This might sound abstract, but it mirrors how the universe actually behaves. In the double-slit experiment, a particle goes through both slits until you measure it, then it chooses one. But if you erase the which path information later, the interference comes back. It's not that the particle hides the truth, it's that the truth never existed until the question was asked. So what about perception? Is what we see real? The colors, the edges, the sense of motion, are they properties of the world, or inventions of the brain? Neuroscience tells us that what we perceive is not raw data, it's a constructed model, a simulation built inside the mind, based on sensory input and memory and prediction. When you see a red apple, your eyes are not detecting redness, they're measuring light wavelength. Your brain converts those into a color experience, something that doesn't exist in the apple itself, it exists in you. Reality, in this sense, is a collaboration between the world and the mind. This is not to say the world is imaginary. The world pushes back. You cannot simply will it into being, But the experience of reality, the version you live inside, is shaped by biology, by context, by expectation. It's filtered, framed, interpreted. This becomes especially clear in altered states of consciousness. Under meditation, or psychedelics, or neurological changes, the brain's default model begins to break down. Perception fragments, time warps, space folds, the self dissolves, and yet something remains, an awareness that there is still something there, but what it is feels entirely different. These moments reveal just how constructed our normal experience of reality is. They suggest that our waking world is just one version of what the brain can assemble, one map, not the territory. Even in dreams, we inhabit fully realized worlds, with logic, sensation, emotion, all created internally. The mind, it seems, does not require external input to generate a sense of place. Reality, at least in terms of experience, can be self-sustaining. But experience is not physics. So let's return to the external, the physical, the measurable. In physics, especially quantum gravity, some researchers believe that space and time themselves may be emergent phenomena, that the smooth fabric of the cosmos arises from deeper structures like entanglement, or spin networks, or causal sets. If this is true, then even geometry is not fundamental. Distance is not a property of space. It's a measure of how entangled two regions are. Areas that are highly correlated appear close. Areas that are uncorrelated seem far. It's not location that defines connection. It's connection that defines location. This flips everything we thought we knew. It says that space is not a stage. It's a consequence, and time too may not be a river, but a sequence of information updates. Reality becomes a process, a computation, an evolving web of relationships. In this framework, reality is not a thing, but a story, a sequence of interactions that give rise to the illusion of a world. What we see, hear, and feel are surface features, the ripples of a much deeper ocean. And here's the most unsettling part. Some interpretations suggest there may be no objective reality at all, that what's real for you may not be real for someone or something else. Not because of illusion, but because reality itself is fundamentally perspectival. This doesn't mean anything goes. It means there is no universal frame from which to say this is what's truly happening. Every observer carries their own slice of the universe, and reality is what exists between those slices, in the overlaps, in the intersections. So what is reality? It may be nothing in particular, and everything at once. It may be an emergent structure, a network of correlations, a self-reinforcing loop of perception and interaction. It may be a hologram, a simulation, a mathematical object, or a story told by physics to consciousness, and vice versa. But whatever it is, one thing seems certain. It is not as it seems. The world we wake up to, walk through and return to in dreams. It's built on assumptions, on rules we never made, but learned to live by. Beneath those rules there is a deeper logic, and beneath that perhaps only questions. Chapter 15. Is the universe made of math? When equations become reality, what if the universe is not just described by mathematics, but is mathematics, not a poetic metaphor, but a literal truth, that everything you see, feel, touch, every particle, every field, every star, is nothing more than a structure, unfolding by the logic of numbers? This is not a new question. From the time of Pythagoras, philosophers have wondered why the world obeys mathematical laws, why a falling apple traces a parabola, why planets sweep equal areas in equal times, why light refracts at angles described by sine functions. Mathematics doesn't just model reality, it predicts it, and the predictions were Isaac Newton's laws of motion and gravitation, written in clean symbols, could predict the orbits of moons centuries into the future. Maxwell's equations described electromagnetism in 4 elegant lines. Einstein's theory of relativity collapsed space and time into a single beautiful formula. At every level, math seems to know more than we do. But why? Why should the universe, which seems physical, messy, even chaotic, behave in ways that are so deeply mathematical? Why should reality speak the language of logic, symmetry, and equation? Could it be because the universe is made of math, and what we see as physical is just how math feels from the inside? This is the bold claim of mathematical universe hypothesis, most famously proposed by cosmologist Max Tegmark. In this view, the universe is not a thing that math describes. It is a mathematical object, a structure that exists outside of space and time, defined entirely by logical relationships. Under this theory, reality is made not of particles, fields, or even information. It is made of abstract structure, of sets, symmetries, and functions. Just as a triangle is defined by its angles and sides, the universe is defined by its internal relations. The difference is that we are part of it, observers inside a system, trying to understand its rules. Let's pause on that idea. If the universe is math, then consciousness, experience, and even free will would have to emerge from mathematical structures. There would be no randomness, only complex relations. You, sitting there, reading this text, or hearing this narration, would be a substructure in the grand equation, a theorem in motion. This sounds radical, but consider this. Physics doesn't care what something is, it only describes how things relate. What matters is how one object moves relative to another, how energy is exchanged, how forces are applied. The identity of objects is not fixed, only their properties and relations are. And mathematics excels at describing relations: a spinning electron, a vibrating string, a collapsing star. Each can be reduced to numbers and rules. We don't know what an electron is, but we know what it does, how it behaves, how it interacts. In physics, this is enough. Some physicists go further. They note that even space and time, once thought to be the backdrop of existence, are now seen as emergent, arising from more fundamental rules. Those rules can be written in mathematics. And if the foundations are mathematical, perhaps the whole structure is. In quantum mechanics, for example, the state of a system is described by a wave function, a mathematical entity that contains all possible outcomes. When we observe the system, the wave function collapses into one result, but between observations it evolves smoothly, according to the Schrödinger equation, a pure mathematical law. Even the strangest behaviors, entanglement, tunneling, superposition, all emerge naturally from math. They are not strange to equations, only to us. Math does not struggle with paradox. It simply follows from assumptions. And then there's string theory. In this framework, the universe is not made of point particles, but tiny one-dimensional strings, vibrating at different frequencies. Each mode of vibration corresponds to a different particle. The theory requires multiple dimensions, not because we wanted them, but because the math demands them. The equations lead and reality follows. Or perhaps math leads because it is reality. Maybe the reason equations seem so powerful is because they are not describing something else. They are describing themselves. When you write a mathematical rule, you are uncovering a piece of existence. But can a purely mathematical object give rise to something like consciousness? Can equations think, feel, wonder? That is the heart of the objection. We experience life as something warm, fluid, irreducible, not as a set of formal axioms, not as a theorem. Yet the brain is physical, the neurons, the connections, the electrochemical signals, all obey physics, and physics, again, obeys mathematics. So if mind arises from brain, and brain obeys math, then the bridge is at least plausible. Consciousness may be a process within a mathematical system, like a ripple in a pond that doesn't know its water. Still, some resist this view. They argue that math is a human invention, a language we made to understand patterns, that numbers don't exist in nature, we impose them, that equations are tools, not truths. But here's the challenge. Math predicts. It tells us things we didn't know, things we later confirm. If math is a human invention, how does it know what's next? When Paul Dirac wrote an equation that merged quantum mechanics and special relativity, it spit out a strange result. A particle with the same mass as an electron, but opposite charge. No one had ever seen such a thing. But years later, the positron was discovered. Math had revealed a truth that nature had kept hidden. This happens again and again. The equations point beyond what we can see. They whisper secrets that experiments later uncover. This suggests that math is not just descriptive, it's ontological. It's the structure beneath the surface, and we are living inside it. Of course, not all math corresponds to reality. There are infinite consistent systems, non-Euclidean geometries, exotic topologies, abstract groups. They exist in logic, but not in nature. So the challenge becomes, why this math? Why these rules, and not others? Why does our universe follow this specific structure out of the infinite ones that could exist? This question is sometimes answered with selection principles, ideas like the anthropic principle, which says that only in universes with the right math can observers arise to ask the question. Others appeal to simplicity, elegance, or symmetry, but the truth is, we don't know. Maybe all possible mathematical structures exist. Maybe each one is a universe, a mathematical multiverse, where every consistent set of rules gives rise to its own cosmos, with its own inhabitants, laws, and truths. We just happen to be in the one that looks like this. It might sound extravagant, but it solves a key problem. It removes arbitrariness. If all math exists, there's no need to ask why this one. All structures exist, reality is math, and math is infinite. But then, who decides what exists? What makes math real? Does it require a mind, a computation, or does consistency alone confer existence? These are deep questions, philosophical as much as physical. But in a mathematical universe, the answer may be simple. If it can be written, it is. So here we are, a conscious ripple in a sea of equations, a fleeting pattern in a structure that may have no beginning, no end, and no author. The universe in this view is not a story told to us. It is a self-existing pattern, unfolding moment by moment, according to rules it cannot help but follow. And us, we are subroutines, logical loops with feedback, mathematical patterns that for a brief moment ask the question, what is this? And in doing so, become part of the answer. Chapter 16, Schrödinger's Cat. The paradox that refuses to die. Sealed box. A single cat, a vial of poison, and a quantum device, triggered perhaps by the decay of a single atom. This isn't a horror story. It's one of the most famous thought experiments in all of science, and it begins not with a physicist in a lab, but with a man named Erwin Schrödinger, who was deeply troubled by what quantum mechanics seemed to suggest about reality. In 1935, just as quantum theory was solidifying its strangest ideas, Schrödinger introduced a puzzle meant to expose what he saw as an absurdity. The cat, he argued, was caught in a situation that defied logic. According to the mathematics of quantum mechanics, the atom, and thus the trigger, the poison, and the cat, could all exist in a superposition of states, the atom both decayed and not, the poison both released and not, the cat both alive and dead. Schrödinger didn't propose this as truth. He intended it as a reductio ad absurdum, a demonstration that something in the theory must be missing. But instead of being dismissed, the paradox endured, not because it was silly, but because it reflected something profoundly real about how quantum systems behave. At the core of this paradox is the superposition principle. In quantum mechanics, systems do not occupy single definite states until observed. Instead, they exist in a wave function, a mathematical description that includes all possible outcomes. A photon can go through both slits, an electron can be here and there, an atom can be stable and decayed. Until measured, the possibilities remain layered, overlapping, coexist. This leads to the question, when does a possibility become a fact? When does a superposition collapse into a single state? Is it when a particle interacts with a detector, when a conscious observer sees the result, or does the wave function never truly collapse at all? The cat in the box brings this question to a head, because unlike particles and atoms, a cat is macroscopic. It breathes, it thinks, it feels. The idea that it could be alive and dead at once, not metaphorically but literally, strikes us as deeply wrong. And yet, by the logic of the equations, this is exactly what quantum theory predicts. Some interpretations try to resolve the paradox by introducing decoherence. In this view, the cat is not truly in two states, rather the quantum superposition quickly becomes entangled with the environment, the air molecules, the box, the surrounding world. This entanglement makes the two outcomes, alive and dead, effectively separate, no longer interfering. Decoherence makes superpositions look classical, but it does not explain why we see one outcome, and not both. Others turn to the Copenhagen interpretation, the traditional view that measurement causes the wave function to collapse. The act of observation forces the universe to choose, but this leads to more questions. What counts as a measurement? Must it involve consciousness? If so, is the cat itself an observer? Does it know if it's alive? And then there's the many worlds interpretation, proposed by Hugh Everett in the 1950s. This theory suggests that the wave function never collapses. Instead, all possible outcomes occur. but in separate, non-communicating branches of the universe. In one world, the cat lives, in another it dies. Each possibility is real, and we only experience one. In many worlds, the observer becomes entangled with the result. If you open the box, you split too, into versions of yourself, each witnessing a different outcome. There is no collapse, no single history, just an ever-branching multiverse of possibilities. This solves the mathematics, but it introduces an infinite cosmos, a sea of realities, multiplying with every quantum event. Some find this elegant, others extravagant, but it aligns with the math, and the math, so far, works. So what does this mean for reality? It suggests that reality at its core is not a sequence of facts, but a web of potentialities, a field of overlapping futures narrowed into experience by interaction. The cat's fate then is not a riddle, but a myth. It reflects our deepest questions about how the quantum world becomes the one we live in. And it's not just cats. Superposition has been demonstrated in ever larger systems. Quantum coherence has been observed in molecules, in superconducting loops, even in mechanical resonators. The boundary between the quantum and the classical, once thought to be sharp, now appears soft, blurred, and mysterious. The Schrödinger's cat paradox also touches on another fundamental idea, the role of the observer. Are we passive witnesses to a pre-existing world, or active participants in its formation? Does consciousness shape the collapse? Or is consciousness itself just another quantum process, subject to the same rules? Some physicists have explored objective collapse theories, which propose that wave function collapse happens spontaneously, based on mass or complexity. In this view, small systems can remain in superposition, but large ones like cats or humans cannot. These theories are testable, and experiments are ongoing, but so far the standard quantum rules continue to hold. The cat in the box is also a metaphor. It represents every moment in which multiple futures are possible, every choice, every breath, every unfolding outcome that could go one way or another. Quantum mechanics tells us that at the deepest level, the universe is not deterministic. It is probabilistic. It evolves by chance and by law. Yet the probabilities are not chaos. They are governed by strict equations. The randomness is structured. The dice, though thrown, obey rules. And that perhaps is the most remarkable thing, that from indeterminacy arises order, from uncertainty a cosmos. Schrödinger's cat continues to haunt physics, because it forces us to confront the boundaries of our theories. It asks, where does the quantum world end, and the classical world begin? Where does maybe become it? It reveals that our language, our intuitions, struggle to grasp what the math so calmly describes. And in doing so it opens the door to new ideas. Perhaps reality is layered. Perhaps observation is interaction. Perhaps what we call collapse is simply a change in perspective, from uncertainty to information, from many possibilities to one experience. Whatever the truth, one thing remains clear: the cat in the box is not just a quirky puzzle, it is a map, a signpost pointing to the edges of knowledge, to the limits of explanation, to the horizon where physics meets philosophy. Chapter 17. The Quantum Eraser. When the future changes the past. Imagine performing an experiment. You send a photon through two slits. It behaves like a wave, producing an interference pattern. Then in another trial, you try to detect which slit the photon went through. Suddenly, the interference disappears. The photon behaves like a particle. Now, imagine you erase that which path information, after the photon has already passed through the slits. And somehow, the interference pattern comes back. It sounds impossible, like science fiction, like time playing tricks. But this is a real experiment. It's called the quantum eraser, and it challenges our very idea of cause and effect. To understand it, we have to return once more to the double-slit experiment, the cornerstone of quantum weirdness. When particles like electrons or photons are sent through two slits, they create an interference pattern on a screen. Even if they're sent one at a time, the pattern emerges over time, as if each particle interferes with itself. This only happens when you don't know which slit the particle went through. If you place a detector at the slits to find out the path, the interference disappears. The particle behaves like a classical object. This has been tested thousands of times. So far, strange but consistent. Observation collapses the wave function. But in the 1980s and 1990s, researchers like Yoon-Ho Kim and others asked, what happens if we delay the choice of whether to observe the path? What if the decision to detect or erase comes after the particle has already passed through the slits? Enter the delayed choice quantum eraser. In this setup, a photon passes through a crystal that splits it into two entangled photons, one called the signal, the other the idler. The signal photon goes straight to a detect. The idler photon, meanwhile, takes a longer, twisted route through beam splitters and mirrors. Depending on how the idler is routed, we may or may not gain which path information. Crucially, this choice is made after the signal photon has been detected, and here's the paradox. When the idler reveals which path data, the interference pattern disappears. But when the idler's path is altered to erase that information, the interference returns, even though the signal photon was already detected. It's as if the future decision to erase or not retroactively changed the behavior of the earlier photon. It's as if the photon knew in advance how it would be measured. But how can that be? How can a measurement in the future affect the outcome in the past? Some argue it's not really retrocausality. The interference pattern is only visible after the data from both photons are correlated. Until you compare the signal and idler results, the pattern doesn't emerge. It's not that the past is changing, it's that the full picture only makes sense in hindsight. The universe isn't rewriting history, it's just revealing how connected everything already was. Still, the implications are profound. The quantum eraser suggests that information, not just observation, is central to reality. Whether or not we could know the path of a particle affects its behavior. Reality responds not to what we see, but to what can be known. This idea places information at the heart of quantum physics. Not as an add-on, but as a fundamental building block. The wave function doesn't just evolve, it encodes possibilities, knowledge, and limits on knowledge. When information is erased, it's as if the choice never existed. The universe rewinds the uncertainty. It also challenges our notions of time. In classical physics, time moves forward, cause precedes effect. But in quantum mechanics, time is more flexible. Entangled particles don't care about distance. And now, they may not care about time either. Some interpretations of quantum mechanics embrace this fluidity. The two-state vector formalism, for instance, views quantum systems as being defined by both initial and final states. The present, in this view, is shaped by both past conditions and future boundary constraints. Time becomes a loop. Events are co-determined. The future is not fixed, but it reaches back. But this raises deeper philosophical questions. What is the nature of time? Is it a flow, an illusion, a dimension we move through, or is time a consequence of deeper processes, of entropy, of information change, of consciousness itself? In the quantum eraser, time doesn't behave like a river. It behaves like a tapestry woven from both ends. What happens now may echo backward, and what happened before may only make sense in light of what follows. Still, we must be cautious. These experiments do not allow us to send information into the past. They do not enable time travel or paradox. What they show is something subtler and stranger, that the structure of quantum reality is non-local in time, just as it is non-local in space. It's not that the past changes, it's that the meaning of the past depends on the future. Until all the pieces are in place, the picture remains incomplete. This is not science fiction, it's quantum fact, tested, verified, repeated, and yet, still not fully understood. The quantum eraser is not just an experiment, it's a glimpse into a world where logic bends, where time may not be a line, but a web, where cause and effect become partners in a cosmic dance. And perhaps, it hints at a deeper unity, a level of reality where time, space, information and consciousness are threads of the same cloth, where questions like when and how dissolve into patterns of relationship, where knowing is becoming, and becoming is the unfolding of all that is possible. Next, we travel to one of the most audacious ideas in modern physics, the notion that space and time may emerge, not from matter, but from entanglement itself. What if space is not where things are, but what arises when things are connected? Let's dive deeper. Chapter 18. Entanglement builds space. The fabric of reality may be information. What if space is not a container, not a stage, or a grid, or a thing that stretches and bends? What if space is not something we exist in, but something that emerges because we exist, because things are connected? This is the radical idea at the frontier of physics, that entanglement, not distance, is what creates the structure of space, that where things are depends not on how far apart they seem, but on how deeply they are correlated. In this view, space is not fundamental, it's a product of information. And the deeper you look, the more the illusion of separateness fades. Let's go back to quantum entanglement, one of the strangest and most beautiful phenomena in nature. When two particles become entangled, their properties are linked. Measure one, and you instantly know something about the other. No matter how far apart they are, the effect is not due to signals or forces or hidden messages. It is a pure, non-local connection. Einstein called this spooky action at a distance, but experiments have confirmed it again and again. Entangled particles behave as one system, even across light years. It's not that one causes the other. It's that they are not truly separate. They are parts of a whole. Now imagine this idea, not just between two particles, but between every part of the universe. A vast network of correlations weaving reality together. In this network, proximity is not about coordinates, it's about entanglement. Two regions of space are close if they share information. If they are entangled, this leads to a startling proposal, that the very geometry of space, its distances, its shapes, its curvature, arises from patterns of entanglement. That space is not a background, but a map of information flow. The more two areas are entangled, the more they are stitched together. And if entanglement is reduced, the fabric of space frays. This idea gained momentum from studies in quantum gravity, especially in efforts to unify Einstein's relativity with quantum mechanics. In these attempts, researchers noticed that certain descriptions of spacetime, especially in curved geometries like black holes, can be re-expressed entirely in terms of quantum information. One of the most influential discoveries came from studying something called the Adair-CFT correspondence, a duality proposed by theoretical physicist Juan Mulder-Seiner. It suggests that a universe with gravity, like ours, can be described by a lower-dimensional system with no gravity, living on its boundary. This lower-dimensional system is entirely quantum, made of entangled quantum bits, and yet it gives rise to a geometric space, a curved world, complete with gravity and motion. In this model, entanglement patterns literally shape space. The more entangled two regions are in the boundary theory, the closer they are in the bulk, the interior of the space. This connection goes even deeper. Researchers like Mark van Ramsdonk showed that when you reduce entanglement between parts of the boundary, the space in the bulk pulls apart. In the extreme case, space rips, like cutting a string. So the very connectivity of space may be rooted in quantum correlations. This is more than metaphor, it's math, it's simulation. It's the idea that entanglement builds geometry, that space is a result, not a cause, that what we perceive as distance is just the shadow of deeper informational relationships. Even the Einstein field equations, the core of general relativity, may emerge from statistical relationships in quantum entanglement. Physicist Ted Jacobson showed that if you assume a few basic thermodynamic principles, you can recover Einstein's equations as a kind of emergent behavior. Gravity, in this view, is not a force, but a byproduct of the flow of information. This leads to a unifying principle that spacetime and gravity are emergent, not fundamental ingredients, but macroscopic consequences of a deeper quantum informational substrate. Like temperature emerges from atoms, space emerges from entanglement, and reality as we experience it is a large-scale illusion built from tiny invisible threads. It also means that information is not just important, it is the fabric of the cosmos. Every bit of reality, every field, every particle, every law is encoded in relationships. The universe doesn't store data the way a hard drive does. It is data, and that data flows, evolves, transforms into what we call existence. In this picture, you are not a point in space. You are a node in a vast informational web. You are connected to everything, not metaphorically, but physically, through entanglement, through interaction, through correlation, and your sense of place of separation is just the shape that information takes in your corner of the cosmos. This also changes how we think about black holes. These mysterious objects where gravity becomes extreme may not destroy information, but scramble it. They may act like quantum processors encoding, transforming and preserving reality in complex ways. Holographic theories suggest that the entire contents of a black hole, even of a universe, may be encoded on its boundary. Just as a hologram encodes a 3D image in a 2D surface, the cosmos may be a projection of underlying entangled data, and that projection is what we call space. So what does this mean for the nature of reality? It suggests that the universe is not a place. It is a process, a computation, a symphony of relationships unfolding over time, and the harmony of that unfolding, the balance of correlation, the rhythm of entanglement, creates the illusion of geometry, of motion, of form, of here and there. Space, in this view, is not the stage. It is the dance. It is what happens when information sings, and when the song becomes coherent, a world appears. A world where light moves, where stars shine, where thoughts arise. And this world, our world, is built, not on substance, but on structure, not on objects, but on relations, not on things, but on the invisible threads that tie all things together. Threads we call entanglement. Threads we can never touch, but which touch everything. Chapter 19. The Illusion of Time. Why the flow may be an emergent dream. You feel it every second. The tick of a clock, the rhythm of a heartbeat, the quiet march of morning into night. Time flows, or so it seems. But what if it doesn't? What if the passage of time is an illusion? Physics, strange as it may sound, has long been suspicious of time. In Newton's world, time is absolute, a backdrop against which everything moves. But when Einstein introduced relativity, that picture cracked. Time became local, relative, elastic. It could stretch, it could slow. Two observers could disagree on what happened first, and both would be right. Relativity teaches us that time is not a universal river, but a fabric. Space-time, not space and time, is the canvas of the cosmos. Mass bends it, motion skews it, and clocks in motion tick differently than clocks at rest. The faster you go, the slower time moves. Near a massive object, time dilates. This has been measured, confirmed. Our satellites account for it every day. But that's just the beginning. As we look deeper into the heart of quantum mechanics, into the fabric of reality itself, something even stranger appears. There may be no flow, no past, no future, no now that moves. Instead, all of time may simply exist already. This idea is known as the block universe. Imagine the universe as a four-dimensional loaf, not a sequence but a structure. The past is one slice, the future is another, but all slices are equally real. What we call now is just where we happen to be inside the loaf. In this view, time does not pass, we pass through it, like a needle moving across a record. The music is already there, from first note to last, but we only hear one moment at a time, and we mistake that unfolding for a flow. This may sound philosophical, but it is grounded in physics. Einstein's equations are symmetric in time, they work the same, whether time runs forward or backward. There's nothing in the math that prefers a direction. So why do we remember the past, but not the future? Enter entropy, the arrow of time. In thermodynamics, systems tend to move from order to disorder. Ice melts, smoke disperses, memories are written, but not unwritten. This rise in entropy gives time its direction, its arrow, not because the laws require it, but because the universe began in a state of low entropy. In other words, time flows because it started ordered, and from that beginning, disorder has been increasing. We remember the past because it was more organized. The future is unknown because it hasn't yet been processed by us. But to the equations, past and future are mirrors. This suggests that the arrow of time is emergent, not fundamental, not baked into the rules, but arising from the conditions of the universe, from the way particles began, from the way information spreads. Some physicists believe that even this arrow may be an illusion, that the flow we experience is a trick of consciousness, the way our brains process change. Just as a film strip is static, but appears to move when projected, our minds may create the illusion of time by focusing on one frame at a time. Julian Barber, a physicist and author, suggests that time does not exist at all. He proposes a universe made of nows, distinct configurations of the cosmos, each timeless in itself. Motion in this view is an illusion. There is no before or after, just a landscape of frozen moments. And what we call a lifetime is just a path through that landscape. It sounds abstract, even unsettling, but it fits, because in quantum mechanics, time doesn't behave the way we expect. In many formulations such as the Wheeler-DeWitt equation, time disappears from the math entirely. It's not that time is hard to define, it's that in some theories it's not even there. This has led researchers to wonder, could time be emergent, just like space? Could it arise from entanglement, from information flow, from the internal correlations of a deeper quantum state? In this view, time is not a fundamental axis. It is a side effect, a useful illusion, like temperature, or color, or sound. Even in cosmology, time gets blurry. Near the Big Bang, conditions were so extreme that our current understanding of time breaks down. The early universe was so hot, so dense, so quantum, that even the concept of before and after may be meaningless. Time, if it exists, may have started there, or may have been something else entirely. Loop quantum gravity, one attempt to quantize space-time, suggests that time is not smooth, but made of discrete chunks. Moments, not a flow. A granular clockwork that ticks not in seconds but in quantum jumps. Between states, between geometries, between possible configurations. This connects back to the idea that the universe is not a place, but a process, an unfolding of informational patterns, and that unfolding, when viewed from inside, feels like time. But from outside, from the equation's point of view, there is no ticking, no past, no future, just the totality, the whole tapestry, woven already. So where does this leave us? If time is not real, why do we experience it so vividly? Why do we age? Why do we remember? Why do we long and plan and regret? Because the illusion is part of the structure. Our biology is built to register change. Our psychology is wired for cause and effect. We are information processing systems, and processing happens over states. That sequence is what we call time, but it may not reflect the deeper reality. Perhaps we are like characters in a book, aware only of the current sentence, but existing throughout the story. The past is not gone, the future is not written, but all of it exists in the author's mind, and the author may be the universe itself. Chapter 20. The Code of the Cosmos. Could reality be computation? Is the universe a machine or a mind? A substance or a simulation? What if reality isn't made of matter or even energy, but of code, bits, logic, pattern? What if everything we see, space, time, forces, particles, is just the surface layer of a vast cosmic computation? This idea may sound like science fiction, but it has deep roots in physics and philosophy. At its core is a question that has haunted humanity for centuries. What is the universe really made of? Ancient philosophers said earth, fire, air and water. Modern science says particles and fields. But in the last few decades a new answer has emerged. Information. The language of ones and zeros. Not just something that travels through systems, but something systems are. In the 1980s, physicist John Archibald Wheeler, colleague of Einstein, mentor of Feynman, proposed a radical idea. When Einstein, mentor of Feynman, proposed a radical idea, we were from bit, that is, everything, every particle, field or chunk of space, ultimately comes from binary choices, yes or no, 1 or 0. According to Wheeler, at the deepest level, reality is not stuff, but questions asked and answers received. The universe is not a solid object, it is a process of information exchange. This vision aligns with quantum mechanics, because in quantum theory, observation creates reality. Particles do not have definite positions or energies until measured. Measurement is an information event, and each such event, each collapse of a wave function is a bit of reality being written. What if this goes further? What if everything, from atoms to galaxies, from neurons to black holes, is part of an ongoing computation, a cosmic algorithm unfolding across space-time? This is the essence of digital physics, the idea that the universe is a vast information processing system, a kind of quantum computer, not running on silicon, but on the very fabric of existence. Some scientists propose that the laws of physics are not just descriptive, but programmatic, that the evolution of the universe is the running of a code. Just like a video game simulates a world from mathematical rules, The cosmos may be generating itself from underlying logic gates and information states, but unlike games on your screen, this program isn't visual, it's ontological, it is reality. This view finds support in quantum computation. Quantum computers don't just crunch numbers, they harness entanglement and superposition to manipulate the foundations of reality. And if we can build machines that compute using quantum laws, who's to say the universe isn't doing the same? Physicist Seth Lloyd takes this seriously. He proposes that the universe is a quantum computer, not metaphorically but literally. In his view, the Big Bang was the initial state. The laws of physics are the program, and the expansion and evolution of the universe are the computation playing out. Every particle interaction is a logic operation. Every change in entropy is a bit flip. Every moment is a calculation completed. This makes the universe finite but vast. Lloyd estimates the observable universe has processed about 10^20 operations since its birth. Not infinite, but unimaginably complex. And yet, if it's computation that implies constraints, just like a video game can't show what isn't rendered, the universe may not contain what isn't computed. So what we call reality may be the visible tip of a much deeper algorithm. And what appears continuous may be pixelated at a fundamental level. This connects to theories like loop quantum gravity, which suggests space-time itself is quantized, made of discrete units like pixels in a cosmic screen. It also relates to the Planck scale, the smallest meaningful length. Below it, space and time lose definition. Reality becomes fuzzy, digital, and this idea is echoed in string theory, where vibrations on tiny loops encode particle types, a kind of harmonic code beneath appearance. But perhaps the most dramatic implication comes from black holes. Physicists discovered that the entropy of a black hole, a measure of its information content, is proportional not to its volume, but to its surface area. This led to the holographic principle that the information describing a volume of space can be stored on its boundary. Think of a hologram, a 3D image encoded on a 2D surface. Now imagine the universe itself is like that. What we experience as 3D reality is a projection from deeper information. In this framework, the entire cosmos could be a vast holographic computation, a system that stores, processes, and evolves data, your body, your thoughts. This moment, all a part of a computation that writes itself as it runs. It sounds fantastical, but it may be the best explanation for why the universe is both ordered and strange, why math describes nature so precisely, why quantum events are probabilistic, yet follow strict rules, because that's what code does. It creates structure from logic, pattern from process, and the laws of physics may be just subroutines in a deeper software. Some go even further, suggesting that what we call the mind is not an emergent effect, but a fundamental aspect of computation. That consciousness is the reader of the code, the interpreter, the experiencer, not outside the system, but entangled with it. This touches on simulation theory, the idea that our universe might be a simulation run by an advanced intelligence. This theory is controversial, but it shares roots with digital physics. The key difference is that digital physics sees the universe as a self-running computation, not dependent on an external simulator. In either case, the result is the same. Reality is logical at its roots, not because it imitates reason, but because it is reason made real. So when you look at a tree, or hear a voice, or feel the warmth of sunlight, you are not just experiencing atoms and fields. You are interacting with a computational pattern that has run for 13.8 billion years. A program so rich it creates stars, cells, and minds, and maybe it's still evolving, still learning, still rewriting itself through us. Next, we explore one final possibility. If reality is information, could there be something beyond the code? A source, a field, a unity beneath computation itself? Let's drift toward the idea of the unified field, a theory that seeks to bind every force, every particle, every truth, into a single, silent equation. The deepest quiet yet awaits. Chapter 21. The Unified Field. The dream of a single equation behind everything. The deeper we look into the universe, the more we crave simplicity. Not because nature is simple, but because hidden beneath the chaos, we often find elegant patterns. One pattern, one rule, one equation to describe it all. This is the dream of the unified field theory, a single framework that explains every force, every particle, every interaction. Not four fundamental forces, but one. Not many particles, but one system seen from different angles. A theory of everything. Not in metaphor, but in precise mathematical truth. Today, we know of four forces that govern the universe. Gravity holds planets in orbit and galaxies together. Electromagnetism lights our homes and powers our thoughts. The strong nuclear force binds protons and neutrons inside atomic nuclei. And the weak nuclear force allows particles to decay, enabling the sun to shine. Each of these forces has its own rules, its own language, its own domain. But are they truly separate, or are they shadows of something deeper? In the early 20th century, Einstein began chasing the idea of unification. He had already shown that space and time are not separate, they are one entity, space-time. But he believed something more profound, that gravity too could be unified with the other forces. He spent the last 3 decades of his life searching for this connection. He never found it. But his search sparked a century of inquiry. Later physicists picked up where he left off. They made progress. Huge progress. Unifying electromagnetism with the weak nuclear force. This led to what we now call the electroweak theory. At very high energies, these two forces appear to be different expressions of the same force, a symmetry that is broken as the universe cools. This success gave physicists hope. If two forces could unite, perhaps all four could. But gravity has always resisted unification. It behaves differently. It's not a quantum force. It doesn't play well with the rules of uncertainty, entanglement, or superposition. While quantum mechanics governs the small, gravity dominates the large. To merge them, we need a theory that includes both. This is what quantum gravity aims to do. To weave together the curvature of spacetime with the probabilistic nature of the quantum world. Several paths have been proposed. Empron's string theory, which says that particles are not points, but tiny vibrating strings. Each vibration creates a different particle, the same way one guitar string can produce many notes. In this framework, all particles and all forces emerge from different modes of string vibration. String theory also includes gravity as one of those vibrations. This is a major success. But there's a cost. String theory requires extra dimensions, not just the familiar 3 of space and 1 of time, but 10 or 11. These dimensions are believed to be curled up, hidden from view, folded into the fabric of reality at scales too small to see. Some call this elegant, others call it speculative, but it offers a mathematical framework that holds all known forces, at least in principle. Another approach is loop quantum gravity, which doesn't use strings, but instead suggests that space itself is quantized. That geometry is made of loops, tiny units of area and volume, woven together like a quantum fabric. In loop quantum gravity, space-time is not smooth, it's granular, and gravity emerges from how these loops connect and evolve. While string theory tries to unify by adding dimensions, loop quantum gravity seeks to unify by breaking space down into discrete parts. Both theories are incomplete. Both have strengths and challenges. Neither has been confirmed by experiment. But both aim for the same goal, to write down a single theory, perhaps even a single equation from which all physics flows. So far, the best theory that unites quantum mechanics with electromagnetism and the nuclear forces is the Standard Model. It describes how particles behave, how they interact, and how the universe evolved after the Big Bang. But the Standard Model does not include gravity, and it has 19 adjustable parameters, masses, strengths, constants. Why these values? Why not others? The Standard Model is powerful, but not final. And so physicists continue the search, not just for mathematical consistency, but for elegance, for a theory that doesn't just work, but feels inevitable. They imagine a single equation that, when spoken aloud, would describe all motion, all matter, all light, all space and time. Perhaps it will be a simple relationship, like energy equals mass, multiplied by the speed of light squared, but deeper, more universal. Perhaps it will describe a single field, whose vibrations become all forces and particles, a cosmic violin playing every note of reality. Some even wonder if the answer already exists, hidden inside math we haven't interpreted correctly, or inside the structure of information. Maybe it's not written in terms of particles and fields, but in terms of entanglement, or symmetry, or geometry. Maybe the universe is not made of things, but of relationships. One hopeful clue comes from attempts to describe black holes. There, we find quantum mechanics, gravity, and thermodynamics all colliding. Black hole entropy, holographic principles, the limit of information storage in a region of space. These clues suggest there is something deeper, a unifying layer that ties together space, time, energy, and information, a place where all laws converge. The ultimate unified field theory may not look like what we expect. It may not be about particles at all, or force, or even space. It may be a description of pure structure, a timeless, placeless, formless reality from which all appearance arises. An equation not about what exists, but about how existence is possible. A blueprint, not of buildings, but of building blocks. And if we ever find this equation, this single law behind everything, what then? Will it feel like an answer, or just a deeper question? Will it explain love, pain, consciousness, or only matter, light, and time? Perhaps a unified field theory will show us not just how the universe works, but why it is beautiful. Until then, we keep listening, we keep looking, not just with telescopes, but with minds. Not just for particles, but for patterns. And perhaps one day, a physicist will sit at a desk and write a line of math and realize, this is it. This is the code that writes the stars. Chapter 22. Frames of reality. Are we living in a quantum snapshot universe? When you watch a movie, what you're really seeing is not motion. You're seeing a series of still frames, images that flicker one after another so quickly that your brain can no longer tell them apart. The illusion of movement is born not from movement itself, but from your perception stitching each moment to the next. Now take a breath and consider the possibility that the entire universe might be working the same way. What if time is not truly continuous? What if the smooth flow we feel from second to second, from thought to thought, is actually an illusion produced by a rapid sequence of frozen moments? And what if each moment is a complete reality on its own, fully formed, fully real, existing independently, like a single frame in an infinite cosmic reel? This idea, strange as it may sound, has deep philosophical and scientific roots. It suggests that what we call the present is not a moving dot, but a static configuration of everything that exists, from particles and forces to thoughts and emotions. Each moment is its own world, its own universe, and our consciousness may simply be flipping through these frames like pages in a book. In classical physics, time is a continuous variable. It can be divided into infinitely small parts, and each event can be placed on a seamless timeline. This idea is intuitive. It matches our experience of clocks ticking, rivers flowing, and hearts beating. But quantum mechanics introduces a different picture, one in which events are not always continuous. Sometimes they come in discrete packets. Energy, for instance, is quantized. Electrons do not glide smoothly between orbits in an atom. They jump, instant, without passing through the space in between. This behavior has led some scientists to wonder, could time also be quantized? Could there be a smallest possible unit of time, a quantum of duration beneath which nothing happens, no change is possible, and time itself ceases to flow? If such a smallest tick of time exists, it would not be something we could experience directly. It would be far too brief, perhaps on the order of what physicists call the Planck time. This is a duration so short that the entire history of the universe could be divided into more moments than there are atoms in the known cosmos. The Planck time is approximately 0.0, followed by 43 zeros, and then 1 seconds. In full speech, it is 0.00000000000000. This is the time it takes light to travel 1 Planck length, which is the smallest meaningful unit of distance. Below this scale, the very concept of space and time begins to blur. Some theorists suggest that at the Planck scale, the universe is not a smooth continuum, but a series of discrete events. Reality in this view is not a river. It is more like a flipbook. Now, consider your own awareness. You feel like you are constantly present, moving forward through time in a steady stream. But what if this sensation of flow is the brain's interpretation of rapid snapshots? Your mind, built to detect change, might simply be sampling a series of static moments and assembling them into a narrative. In this way, consciousness may act like a projector, stringing together the frozen frames of existence to create the illusion of continuity. Each frame contains a full picture: your body in space, your thoughts in motion, your world appearing to move, but in reality, nothing is moving at all. This concept is related to what some physicists call the quantum Zeno effect. It states that if you observe a quantum system frequently enough, you can actually freeze its evolution. The system stops changing, as if caught in a loop of static observations. In other words, rapid enough measurement can stop time for a particle. This behavior raises a powerful metaphor. Is the universe constantly measuring itself in a way that produces a succession of moments, but no actual in-between? Philosophers have long debated whether time is something real or something imagined. The ancient Greek philosopher Zeno questioned motion itself, arguing that if time were made of indivisible moments, then nothing could ever truly move. Modern physics, surprisingly, has started to ask similar questions. Are we living in a continuous universe, or is our reality made of quantum frames? In the block universe model of spacetime, past, present, and future all exist simultaneously, like slices in a loaf of bread. Your birth, this moment, and your last breath are all part of the same object. There is no now, there is no passage, there is only structure. If this model is accurate, then what we perceive as time passing is simply the experience of one frame giving way to the next. Your conscious mind experiences now as the intersection point of awareness with one static moment, but that awareness never moves. It simply exists, frame after frame, with memory giving the illusion of continuity. Some interpretations of quantum mechanics, particularly those that use the concept of decoherence, suggest that multiple versions of reality exist in parallel, each representing a different possible outcome. What if each of those outcomes is its own frame, its own still image in the multiverse of moments? Imagine the universe not as a movie playing forward, but as an endless gallery of photographs, each representing a frozen instant. Some frames show you awake, others show you asleep, some show you dreaming of galaxies, others show you worrying about bills. Your life then is not a story being told, it is a collection of portraits, and consciousness is simply the part of you that looks at one portrait at a time. This may seem bleak, as if it removes the richness of life, but in truth, it may do the opposite, because if every moment exists eternally, then nothing is ever truly lost. The love you felt, the laughter you shared, the kindness you gave, each of those is a frame forever preserved in the deep architecture of the cosmos. And if our perception of time is just that, a perception, then we have already experienced infinity. Each moment you are in is complete, full, enough. What would it mean to live in a universe made of moments? It would mean that time is not a resource to be spent, but a perspective to be explored. It would mean that movement is a trick of memory, and identity is the thread your mind uses to connect disconnected frames into a single self. It would also mean that death is not the erasure of time, but the closing of the last page in a book that was always complete. Each second you live is its own chapter, and together they make up the story of you. So as you lie in the quiet tonight, and you feel your awareness drifting, remember this: you are not falling through time, you are resting in it. You are a stillness that remembers motion, a dream that imagines a world turning. And whether time is real or not, you are here, now, in a frame that will always exist. Chapter 23: Consciousness and Collapse. Does the mind shape the quantum world? In the quiet spaces between observation and reality, a mystery waits, one that has puzzled physicists and philosophers alike for over a century. At the core of quantum mechanics lies a strange and delicate question: does the world exist on its own, or does the act of looking bring it into being? When you observe something in the quantum world, you do more than just passively watch. You change it. A particle that was in a cloud of possible positions suddenly appears in a specific place. A photon that was undecided about going left or right commits to one path. This shift is known as wave function collapse, a sudden, irreversible change in the state of a quantum system, triggered by measurement. But what exactly counts as a measurement? Is it the interaction with a machine, a detector, or a mind? This is where science touches the edges of philosophy, because while the equations of quantum mechanics tell us how a system evolves over time, they don't explain why a particular outcome occurs when an observation is made. They only give probabilities. Before measurement, a particle exists in a state of superposition, a blend of all possible outcomes, but when observed, only one possibility becomes real. This raises a question as strange as it is profound. Does consciousness itself cause the collapse of the wave function? This idea, known as the consciousness causes collapse hypothesis, has been debated since the early days of quantum theory. It suggests that a conscious observer, a thinking, aware being, plays a fundamental role in shaping reality, not just witnessing it, but helping to select which version of it becomes real. In this view, the world we experience is not entirely objective, it is participatory. Reality is not something that simply unfolds in front of us, but something that we co-create moment by being aware. One of the earliest advocates of this idea was John von Neumann, a mathematical genius who laid the foundations of quantum logic. He argued that the measurement chain from particle to detector to brain must end somewhere, and the only place where the chain can terminate without another physical interaction is the conscious mind. This means that your awareness, by perceiving a result, completes the quantum event. Without your mind, the event remains unresolved, just a cloud of probabilities. Eugene Wigner, another prominent physicist, took this further. He proposed a famous thought experiment, Wigner's friend. In it, a friend observes a quantum event inside a sealed room, while Wigner waits outside. From the friend's perspective, the wave function collapses, but from Wigner's point of view, until he opens the door and asks the friend what happened, the entire room, including the friend, remains in superposition. This leads to a deeply unsettling conclusion, that reality itself may be relative to each conscious observer. This view has both supporters and critics. Some find it elegant, a way to explain why we experience a definite world despite its underlying uncertainty. Others see it as metaphysical, a move away from testable science toward unprovable speculation. Still, the question persists. What role does the mind play in shaping the quantum world? There are alternatives. Some interpretations of quantum mechanics avoid the need for consciousness entirely. The many worlds interpretation, for example, suggests that every possible outcome of a quantum event actually occurs, but in separate, parallel universes. In this view, the wave function never collapses, it just branches. When you measure a particle, you don't choose one outcome. You split into copies, each version of you observing a different result in a different universe. This removes the need for consciousness as a special mechanism. But it creates an infinity of realities for every decision, every interaction, every quantum twitch. Another interpretation is decoherence theory. This says that collapse is not caused by observation or consciousness, but by interaction with the environment. When a quantum system interacts with a large number of particles, say the air or a measuring device, it becomes entangled with them in a way that prevents interference. The superposition spreads out and becomes indistinguishable from classical reality. But even decoherence does not fully explain why we observe a single outcome. It explains how superpositions become unobservable, but not why only one version of events enters our awareness. And so we return to the mystery of the observer. Is the mind just another quantum system, responding to inputs and following physical laws? Or is it something more, a fundamental element of the cosmos that bridges potential and reality? Some scientists suggest that consciousness may itself be a quantum phenomenon, that the brain does not merely compute, but coherently oscillates, sustaining quantum states across networks of neurons. This theory, called orchestrated objective reduction, was proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They argue that microtubules, tiny structures within neurons, could host quantum processes that collapse in a meaningful, non-random way. In their view, consciousness is not just an emergent byproduct of biology, but a deeply embedded aspect of the quantum fabric. If this is true, then consciousness and quantum mechanics are not separate domains. They are intertwined, one giving rise to the other. It's important to note that this theory is controversial and not widely accepted in mainstream neuroscience. Many researchers believe that quantum effects in the brain would be too fragile to persist amid the thermal noise of biological systems. Yet the question remains, why does measurement matter? And what transforms a quantum possibility into a lived experience? Some go even further, suggesting that the universe itself may be conscious, not in the sense of having thoughts or desires, but as a kind of informational self-awareness. This is called panpsychism, the view that consciousness is a fundamental aspect of all, existing in varying degrees. Under this view, particles and fields are not just carriers of mass and energy, but bearers of awareness. Not thoughts, but qualia, the feeling of being something. This would mean that consciousness is not something that emerges late in the universe's history, but something that was present from the start, woven into the equations of existence. In such a universe, observation and awareness are not afterthoughts, they are primary. Whether or not the mind causes collapse, one thing is clear: the act of observation changes what is observed. This is not a metaphor, it is a measured fact. In the quantum world, knowing changes being. Even if the conscious mind is not the direct cause, it is still the lens through which reality becomes experience. Your awareness may not shape the particle, but it shapes the world you live in. So, tonight, as you rest and drift, remember that your mind is not merely watching the universe. It is part of the equation, not separate, not above, but within. The observer is also the participant. The mind is not a light shining on reality. It is a mirror, reflecting the wave into a world. Chapter 24: The Edge of Reality. What happens at the boundary of physics and consciousness? When you push against the outer walls of scientific understanding, you don't always find answers. Sometimes you find mirrors. And when you look into them, you no longer see atoms and particles. You see awareness looking back. At the edge of physics, where quantum theory dissolves into probability, where space warps under gravity, and where time begins to lose meaning, a deeper question emerges. What happens when we stop treating consciousness as a side effect and start seeing it as part of the equation? Throughout history, science and consciousness have been distant neighbors. Physics focused on the measurable forces, fields, and formulas, while the mind was left to philosophy, psychology, or metaphysics. But now, as we reach into the deepest layers of reality, these two paths are beginning to curve toward each other. To understand the edge of reality, we must ask what reality truly is. Is it the sum of all particles? Is it the space-time fabric they dance on? Or is it something deeper, an invisible scaffolding that connects observation with existence? Quantum mechanics has already shown us that the act of observation changes what is observed, not just in theory, but in experiment after experiment. A photon passes through both slits when unobserved, but chooses a single path when measured. Reality responds to awareness. But how far does that reach extend? Some thinkers believe that this connection between observation and outcome is not a coincidence, but a clue. They propose that consciousness may be entangled with the universe in ways we do not yet understand, that the mind is not a passive spectator, but a co-author of the unfolding world. One idea is that reality does not exist independently of awareness. Instead, it may emerge through a dynamic relationship, a kind of resonance between the observer and the observed. This is more than philosophical poetry. It is an open question in physics, especially in the search for a unified theory of everything. Current theories describe particles, forces, fields, even the expansion of space, but they do not include the observer. They do not describe the part of the universe that is asking the question. And yet, without observation, we have no phenomena, no data, no experience. What is a universe without anyone in it to know it exists? Some models, like the participatory anthropic principle, suggest that observers are not afterthoughts, they are essential. But the conditions of the universe are shaped in part by the requirement that someone must be here to ask why. This may sound circular, but perhaps that's the point. Perhaps the universe folds back on itself in a loop of knowing. Modern neuroscience tries to explain consciousness as the result of complex processes in the brain. Neurons fire, chemicals flow, and somehow experience arises. But this model has limitations. It explains mechanisms, but not experience. It can measure brain activity, but not the feeling of being. And when we search the equations of physics, we find forces and fields, but not the color red, not the taste of salt, not the ache of memory. These things do not show up in formulas, yet they are the most immediate part of existence. So, what if physics has a blind spot, not a flaw, but a boundary? a place where mathematics ends and awareness begins. Some researchers believe this boundary is not a wall, but a bridge, that consciousness is not beyond science, but the next frontier of it. Theorists like Donald Hoffman propose that the world we see is not the world as it is, but a user interface, a simplified, symbolic dashboard evolved by the brain to survive, not to reveal truth. In this model, space, time, and objects are like icons on a computer screen. They are useful, they are meaningful, but they are not reality itself. Just as a folder icon does not resemble the actual code inside the hard drive, what we perceive, a rock, a chair, a star, may be a simplified representation of something deeper, stranger, and unseeable. If this is true, then physics is not describing the furniture of reality, but the furniture of our interface, and consciousness is not a product of the interface, but the agent who uses it. This turns the usual picture upside down. Instead of matter producing mind, mind may be the source of matter's appearance. Instead of the universe giving rise to observers, observers may be shaping the universe into what can be seen, touched, and measured. This does not mean that reality is a dream. It means that what we call physical may be only one layer, the layer that becomes visible when viewed from within a conscious mind. At the edge of physics, we begin to lose language. Time becomes distorted. Particles become clouds of probability, and consciousness remains the one thing we cannot remove from the equation. No experiment is ever done without an observer interpreting the results. No measurement exists without awareness. Perhaps this is why the final theory of everything remains out of reach. Perhaps we have been trying to build a map without including the one holding it. In mystical traditions, there is a concept of unity, that mind and world are not two, but one, that the distinction between the observer and the observed is an illusion created by the limits of our perception. Strangely, quantum physics seems to hint at the same conclusion, that separateness is not fundamental, that entanglement is not rare, but universal, that the edge of the particle is not where it ends, but where its connections begin. When a quantum particle becomes entangled, its state can no longer be described independently. It becomes part of a system, a relation. Even if you separate the entangled particles by light years, measuring one still affects the other. This is not science fiction. This is verified fact, and it suggests that the universe may be a web of interdependence, a single, inseparable process playing out in infinite forms. So what happens at the edge of reality? Perhaps nothing ends. Perhaps everything meets. Perhaps that edge is not a boundary, but a seam, where physics and consciousness fold into one another, where equations give way to experience, where space becomes silence, and where time becomes stillness. As you close your eyes, you are not drifting away from the universe. You are returning to it, to the awareness that holds it, that dreams it, that reflects it. You are not outside the mystery. You are its edge. You are its center, and you are the silence from which it speaks. Chapter 25. The Silence Between Worlds. What lies beyond the limits of human perception? Close your eyes. Imagine a place where your senses cannot follow. A space beyond color, beyond sound, beyond thought. This place does not exist in darkness. It exists in something even quieter, a silence not of absence, but of too much presence. So vast, so complete, that it slips through the net of perception entirely. The human body is extraordinary, but it is also limited. You see only a narrow sliver of the electromagnetic spectrum. You hear only a specific range of vibration. You touch only what your nerves allow. You taste and smell just the chemical traces that trigger memory. And your mind, remarkable as it is, can only process a fraction of what actually surrounds you. The rest, the ultraviolet dances of distant stars, the deep pulses of magnetic fields, the subtle rhythms of particles weaving in and out of coherence, they all pass by unnoticed, beneath the radar of human awareness. And yet, they are there, always. The cosmos is not small, it is not quiet. It is overflowing with signals. But your brain filters almost all of it out. Not because it is lazy, but because it must. To survive, your awareness must focus. It must ignore the infinite, to grasp the essential. But what happens when we ask, What lies beyond that filter? What structures might exist just outside the range of perception, structures that do not shine, do not speak, and cannot be felt, but nonetheless shape the entire architecture of reality? Physicists have long suspected that much of the universe is hidden from view. They call it dark matter and dark energy, mysterious ingredients that together make up over 95% of the cosmos. We cannot see them, we cannot touch them, and yet we know they are there because of how they bend space, how they influence the motion of galaxies, how they hold the universe together. In this invisible realm, things do not behave like the matter we know. They do not emit light. They do not scatter particles. They whisper across the fabric of existence, like wind pressing against a closed window. Felt, but not seen. Present, but not known. Now imagine this hidden matter is only the beginning. What if there are entire layers of structure, not yet theorized, dimensions curled too tightly to detect, realities operating on different speeds of time, or laws of physics that only emerge under conditions we cannot replicate? Some physicists believe we may live in a multiverse, a vast field of possible realities, each with its own version of physics. In one, gravity may be stronger. In another, atoms may never have formed. And in still another, someone like you may be listening, but with a body made of entirely different matter. Our tools, telescopes, microscopes, colliders, extend our reach. But even they have limits. They translate invisible signals into visible ones, interpret silence into equations. Yet beneath that, beneath the particles and probabilities, there may be a realm so subtle, so foundational, that it cannot be decoded except through consciousness itself. This is not mysticism, it is humility. It is the recognition that the known is only a shadow of the knowable. There may be frequencies we have not yet invented machines to detect, particles we have not yet found names for, fields that vibrate so gently they never register as matter, but instead shape the laws that govern matter itself. And perhaps, just perhaps, what we call silence is not emptiness, but information too vast to measure. Some researchers are beginning to ask whether perception itself is a fundamental tool of science, not just a subjective bias, but a mode of participation in reality. They ask, is it possible that certain truths can only be grasped by presence, not by detection, but by aligning consciousness with the structure of what is beyond words? This idea does not discard physics, it expands it. Because even within physics, there are uncertainties so deep they begin to resemble silence. Take the Heisenberg uncertainty principle. It says, you cannot know both the position and momentum of a particle with absolute precision. The more you know of one, the less you know of the other. This is not a limitation of measurement. It is a feature of the universe itself. Built-in ambiguity, structured silence. Reality holds part of itself back. And perhaps that is not an accident. Perhaps the cosmos leaves gaps, not to frustrate us, but to allow mystery to live. Mathematics too reaches limits. In the early 20th century, Kurt Gödel proved that any formal system contains truths that cannot be proven within that system. This means that logic, even at its most precise, cannot fully explain itself. There will always be truths that live just outside the edge of proof. Is it possible that consciousness is one of them? Not an illusion, not an error, but a truth, so close to the source that it cannot be separated from the field it seeks to understand. In this sense, the silence between worlds may not be a wall, but a bridge, the space where understanding does not arise from facts, but from attention, where knowledge does not emerge from data, but from stillness. Some philosophers suggest that what lies beyond perception is not more matter, but more meaning, that the universe is not just a machine, but a message, and that silence is the grammar in which it is written. This silence is not a failure of language. It is the space in which language becomes possible. It is the interval between thoughts, the breath between words, the pause before the wave function collapses, and in that pause, there may be a kind of knowing that does not require definition. Perhaps the silence beyond perception is not something we need to break. Perhaps it is something we need to honor, to sit with, to breathe into. As you drift tonight, you do not drift away from the world, you drift deeper into it, into the parts of it that do not shine or speak, but still shape everything. The silence between worlds is not a void, it is a presence too wide for our senses, too quiet for our language, and too rich for our measurements. So what lies beyond the limits of human perception? Possibility, depth, a sea of structures we cannot yet imagine, a field of being that vibrates in frequencies too delicate for instruments, but perhaps not for awareness. And maybe that's the final mystery, that the most advanced detector the universe has created is the mind, not to dominate the unknown, but to listen for it, to feel its edges, to lean into the pause, and to let the silence